because AIMagn was founded in Rome by Dino Fiorani. And then, I mean, we are very happy that the association is still progressing and that the work of Dino has been, I mean, let's say, it take presence also today. And I'm very happy that Gaspar is vice president of the association, of course. Okay, I should not say so much. The point is that so a few years ago, when I arrived in Genova, I have this idea to bring Mössbauer spectroscopy in Genova. So I fight a little bit as usual, and but we got some money from the university, and then after 2 years, we succeed to have the spectrometer, not yet the source, but someone is telling me that is coming. And the point is that, so this workshop, let's say, it represents the scientific start of this adventure. To be honest, yesterday I was a bit realizing that, so for sure, I will just start this adventure, but I will not complete it because someone else will take care of this in the future, because it's quite a long way to establish an expertise here. And then I'm very, very happy that Sosen will take care of this journey. So, and then I have to introduce Jean-Marc Greneche. To be honest, I was thinking how to say about Jean-Marc, because so to say that he's an expert on Mössbauer spectroscopy is probably too easy. But for me, for my generation, Jean-Marc, it represents a part of a generation of scientists that sign a milestone in nanoparticle magnetism. I would like to remember some other French scientists like Jean-Louis Dorman, Elisabeth Tronc, Jean-Pierre Jolivet, and of course Dino. Dino was part of the team because he was working with Jean-Louis Dorman for many years. And so Jean-Marc represents a continuous of this generation because, of course, he's an expert in Mössbauer spectroscopy, that's for sure, but give fundamental contribution in nanoparticle magnetism. So there is a lot of papers, milestone of Jean-Marc about nanoparticle magnetism generation. Me and the other generation working on this were basically focused on this. Then it's really a pleasure to have Jean-Marc here in Genova. And of course, I cannot spend so much other words, just giving you the floor, Jean-Marc, to give your plenary talk today. Thank you very much for coming.
Thank you, Davide. So, of course, I want to say first, congratulations to the magnetism community of Italy, because it's very important to establish some contacts, to work together. And it's, to my point of view, it's very important. In French, we had what we call GDR, Groupement de Recherche, research assemblies on one topic. And it favors the communication with some small meeting once or twice per year. And I think it's very important for people to discuss the aspect of what are the main topics, what about one topic, what about the different techniques. So congratulations for this. And I want to say also about Mössbauer. So maybe not a kind of state of art. So as I mentioned before, there was a development, the major development was in 70s and 80s. And there were many groups, as Davide mentioned, about, for example, Jean-Louis Dorman in Paris, and Elisabeth Tronc. Jean-Louis was working especially on Mössbauer, a bit of on magnetic measurements. So there was some laboratories, they were devoted only to one technique. And the science has moved in 90s, so it was not possible to propose some project based on one technique. But it was necessary to have some physical objectives. For example, I don't know, I would say multi-layers, spintronics, and so on. So that means progressively there were less importance to the techniques, especially as someone from CNRS told me once, Mössbauer is a very old technique. And I heard 2 years ago, 2 years after, he was developing himself the technique. So the main problem, as I mentioned before, it's necessary to be very clear about the physical meaning of the different hyperfine parameters. You cannot use a technique, typically as Mössbauer, by starting each Friday at 4 p.m. and to finish at 5 p.m. It's necessary to go in depth if you want to get many information. And for this, for example, I am considering in France, there were roughly 30 Mössbauer groups in France. Now there is about 5, maybe 4. Because there was a problem. When you had to get a new associate professor, so he is specialized in Mössbauer. No problem. He is specialized in spintronics. Yeah, we are very interested. So it's the change of the strategy in science, and so it's very important. But of course, sometimes people is interested to have information using Mössbauer. So that means it's necessary, and I would suggest, because I suggested in France, to have some platform, kind of national platforms, for which you will have a few persons, few experts devoted to Mössbauer. And if someone is asking to have some problem, he will phone to the platform, well, not to the platform, but to the expert in the platform. I want to do this, this, and this. Is it possible to do experiments and so on? So this is very important. Because, yes, I think in addition with ESRF, in a few years, probably in France, there will be 1 or 2 Mössbauer labs, in the sense that most of people now is retired, as myself. So I want to give a few words about where Nader and myself are coming from. So, okay. So we are coming from Le Mans. So Le Mans is a city which is less important than Genoa, because there is only 150,000 inhabitants in the city itself, and 200 in the community of Le Mans. So we have an old city with a nice cathedral. We have also a Roman wall, very close to a river, and close also to the old city. We have a very famous abbey there. Of course, we have sport. So now Le Mans will be again in the first league of France. So I don't know if it is a good information for taxes, but it's another problem. So you have also some old houses. We have, in addition to the football, we have basketball. So the level is quite good, a priori. We have wine, not so far from Le Mans. And of course, we have the famous 24 hours of Le Mans. So we have not the 24 hours of Mössbauer, but we have the 24 hours of Le Mans. Also, you have to consider that it's not only for cars, it is also for motos, it is also for bikers, and it is also for rollers. So rollers, for those who are interested, I can give you some information about the 24 hours of rollers. But it's very important. I will take a few minutes, maybe, so you are not angry. So maybe there will not be time for eating today. Sorry. Now for rollers, it's very nice because at the beginning you have about 10,000 roller skaters. They are my team of 10 people. And the departure is, they have a kind of, no. Okay, sorry, yeah. So, yes, they have some sensor with a magnet to register the number of loops because they were doing a lot. For those who are in a team of 10 people, they can do 850 kilometers per 24 hours. So that means if you want to go, you have to be well prepared. So there were some people, they are doing a team of 2 people, and sometimes, as for Mössbauer, they were single. So doublet or single line. doublet or single person. And for those who are doing alone, because you can see when you arrive, they were going very fast, and sometimes you can see another one much slower, of course, because he is unique in his team. And finally, he is able to do more than 450 kilometers alone during 24 hours. Okay. And the people is coming from everywhere in the world. And the advantage compared to autos, sound. It's less sounding. Okay. And this weekend will be the next 24 hours of Le Mans. Okay, so we have to go very fast to do Nader. Okay. So now I will speak a bit about Institute, where we are coming from. So Institut des Molécules et Matériaux, I probably, because French is not so different from Italian, you can understand. So this institute belongs to university and also to CNRS, which is a cousin of CNR. So you can see about the number of people who is in this institute. And we have different support from region, from Europe, from Sarthe, which is a district of Le Mans, and from the city, and also from the Ministry of Education, with a large quantity of money, probably as in Italy, and also from CNRS, for which the support is decreasing each year. So the topics, so because at the beginning there were 4 different laboratories, 3 of chemistry and 1 of physics. So they were, the idea was to unify these 4 laboratories. And since the topics were totally different, it was very interesting to have some common interest, because the interest is material science. And it is very interesting to combine physicists, chemists, physico-chemists, and chemical physicists. And also to have to mutualize some equipment, as we will see just after. So you can see what about polymers, organic synthesis, inorganic chemistry. And in physics, we are very focused on the physics of confined systems, and especially in our case with Nader, on magnetic nanostructures, as you will see now and after. But it was also a very interesting group who is working with photo-induced ultrafast dynamics on nonlinear optics. So we have many equipments. That means we have to pay a lot, because the maintenance is not so easy. And we have to do with liquid helium, for example, which is now not a very not low price, and it's very difficult. So I think that Davide has to take into account that it's very important to consider what about the maintenance after of the Mössbauer facilities. I would suggest to have possibility to have a technician to help you. It's very important. And we had a good technician. For example, the cryophones I showed you before, and we will see after the use, has been built by the technician. So we have, for example, good facilities for X-ray diffraction, because for X-ray diffraction, we have for monocrystalline samples, we have for others, for multi-layers, for thin films. So it's possible to do reflectometry, and after we can go to ESRF. For spectroscopies, there is EPR, liquid NMR, solid NMR, and of course, Mössbauer. So for the ultrafast phenomena, they have femto, pico, second laser. Sorry, terrestre. So now they are close to get atto second laser. Okay, so we have facilities also for doing some computing. On the interest, it was 25 years ago, we developed the first PC clusters available in a laboratory without a large quantity of money. And it was very interesting. And we have, in most of spectroscopies, the interest to develop by ourselves the different programs, because we know what is there in the program. Because if you buy the program, it works very well. But after what you are doing to do, if you want to change something, it's very difficult. Okay, so I presented the first part this morning. So now I will try to show you what about some applications in crystallography and so on and so on and so on. So the first case, just an example to see what about the resolution of the Mössbauer technique. One sample coming from the laboratory of fluorides. So you have the composition there. So we are very happy. A single doublet, iron 3+. So now the idea was to find some phase transition. Because they were suspecting. So the phase transition, that means we have to do some measurements versus temperature. We were using the cryofurnace to perform measurements above and below room temperature. So that means from 77K up to 600K. And what we found, for example, for the red curve, the evolution of isomer shift, which decreases when the temperature is increasing. Okay. And after, for the evolution of the quadrupolar splitting in the green one. And, no problem. But if now we look carefully about the green line, which is transformed in the red line, so we can see two steps. We have iron 3+, 3d5. So that means the contribution is only the network. So if there is a change in the value of the quadruple splitting, that means there is a change in the structure. And of course, to tell the truth, I made the first series of experiments and I was a bit doubtful. I repeated it in order to check it was really 2 steps. And of course, because you can see the values of the quadrupolar splitting, 0.62, 0.63, and so the error bar is very, very small. So you have also to consider that we have a single doublet. It's very easy to fit it. And now the idea is to look about the structure. And of course, the Mössbauer does not give information about the evolution, but it was supported by X-ray diffraction. And it was possible to see that at high temperatures, the gamma phase, the change between gamma and beta phase by decreasing the temperature, it was only a kind of the octile one were not dancing samba, they were fixed. And after, the other phase transition was a change of one atom in the unit cell. So that means we are extremely sensitive to the environment. Okay? So now you can see it's a previous MOF. I will speak more in details after MOF. So if you look carefully about, it is a unit cell. If you look carefully about the different species, so you have octahedral, you have tetrahedral, and you have hexahedral units. So of course, we do some Mössbauer spectrum, and you can see that a priori, the Mössbauer spectrum is very simple. But this simple, no, because you have to consider different components to describe it. So of course, if we put 1 component, 2 components, 3 components, it does not satisfy the experimental spectrum. But from 4 components, it's perfect. 4 components, 4 iron sites. Wow, it's good for the crystallographist. And after, we can look, if you look carefully, you can see 3 doublets on the single line, which is broadened, but the barycenter of these doublets are not the same. Barycenter, isomer shift. Isomer shift means neighboring. And of course, it is possible to establish a relation, 2 octahedral sites, 1 hexahedral site, and 1 tetrahedral site. In addition, we have the proportions. Without any constraint during the fit, we were obtaining, I do not remember, but something about 25, 26, 24, 25%. That means they were equiprobable, perfectly in agreement with X-ray diffraction. And going to low temperature at 4K, we can see that we have a phase transition. You can see 4 doublets, 4 sextets, and we can conclude the same about isomer shift and proportions. That means that the Mössbauer spectra were supporting perfectly the results of X-ray diffraction. So now we have the 2 samples, and as you can see, the second one loses water molecules. It was possible to obtain the 2 samples directly, but it was also possible to see what about the evolution versus temperature of these water molecules. So that means the two spectra, they are totally different. And now the question is how to measure. Because, as I did not mention maybe this morning, but the time to get the spectrum might be from 15 minutes up to a few days. It depends on the content of the sample, on the complexity of the structure. So what we are doing now, we were using the cryofurnace, because if we do experiment, for example, at 100 Celsius, and then at 120, probably during the registration, we will accumulate different states. So the idea was to go at one temperature, to stay 1 hour, and to go down at 77 K, and to compare the different hyperfine structures for the different temperatures. Okay? And this is given there. And you can see here, the first spectrum is very close to that one, and the last one is very close to that one. And after it was possible to describe such spectra by considering 8 components, and we can see, because it was a question, because that the evolution is very soft, monotonous, and there is no intermediate stage. So the water molecule is going out progressively. So this is a more recent study. 2013, no. So we had the chemist. We have a mixed system, iron 2 and iron 3. 50-50. Sure. Okay. So can you do Mössbauer spectrum? Well, yeah, why not? With iron, it's easier. No iron is not difficult. It's much more difficult. So when we looked at the spectrum at room temperature, so first you have 3 lines. How to describe these 3 lines? So of course, you have 3 main lines, which can be divided in 4 lines with the same intensity, because it is a powder. So now, how to associate the different lines? Because you have different solutions. And if you look the chi-squared, you cannot distinguish. So you have such a solution, there is no physical meaning. You have another solution, and the last solution corresponds to this one. So what we were going is to go at lower temperature. So 77 K, the system is magnetically ordered. So we limit ourselves to 100 K, just above the magnetic ordering temperature. And of course, this solution was the best one. So now the problem is 53-47. Oh, it's not possible. I'm sorry, but usually Mössbauer is right. Okay, so because they have to do some neutron diffraction experiments, they made 4 batches to get enough sample for neutron experiments. And for me, at each batch, I made Mössbauer spectrum. And for all of them, 53-47. So it's not a perfect mixed system. And finally, of course, the interpretation was done with a kind of deprotonation of this molecule and to satisfy the content of iron 3 and iron 2. So that means it was possible to better estimate the composition of the sample. And finally, they introduced this composition to fit again the X-ray pattern, and it was much better. Okay. So, as I mentioned before, so we have some ferrites. So the composition is with gadolinium or samarium. And it is clear that we perform at room temperature nanoparticles, so plenty of components without physical meaning. Okay, to describe, but it was not possible to distinguish carefully and accurately tetra and octa. The spectrum at 77 K, so we can see some shoulder. Wow! It's possible to put 2 components and to have directly proportion of tetra and octa. But maybe it should be better to perform in-field Mössbauer spectra, according to what I mentioned before break. So we had a spectrum very well resolved. And finally, the proportions, I do not remember exactly, if they were 60-40 finally they were 40, 60. And we repeated the fit with this result. Sorry, okay. By considering the result here, we repeated. And it was also well fitted. So it confirms what I mentioned this morning, that it's necessary to perform in-field Mössbauer experiment to get really the proportion of tetra and octa. Sorry? Okay. So according to MOF, so metal organic framework, so the question was, is there any water molecules inside the pores? So according to the chemist, they are perfect. They are clean. Okay. But sometimes a student came to me and I have a system there with one single iron site. I'm surprised because there is two doublets. Okay. So she was looking and a few weeks after, she told me maybe there is a few water molecules by considering the electronic map. Okay. So what I had done, I use again the cryofurnace. So we increase the temperature and we repeated the spectrum inside the cryofurnace in situ to get the new spectrum. And you can see a decrease of the doublet. So that means that, of course, there was water molecules. And after we put the powder out of the cryofurnace during one night, on the day after, we made a spectrum and we recovered the first spectrum. That means the system was able to breathe, to take water, to expel water, to take again. So now another example. So check carefully the lines. So again, we have two lines, but after the minor component only is there. The major component disappears. Okay? So we made the same, the sample out, and we found again something close to the first spectrum. So that means in this case, the system was full of water. Okay? It was a sponge. So it was not possible to detect by using X-ray diffraction. Okay. So now if we consider this system, neodymium iron boron, so of course it's quite complex. There is 6 different iron sites. So of course, the Mössbauer spectra are very complex. Here you have a series versus temperature. So it was possible to fit, and the best fit was well corresponding to the content of the different iron. That means 50-50, 25-25, and 12.5, 12.5. Okay? And of course, this sample was used by Mike Coe. So I have seen that he was coming for spintronics, but Mike was working a lot during 80s and 90s on this rare earth magnets. And the structure versus temperature versus rare earth to study the spin orientation, to study the oxidation, and more recently to study versus the type of preparation and about nanostructures. So there is plenty of data. And actually, I am working with some Chinese, and they are working with this. And the system is to check what about the nanostructure and to find some structure in between the grains of neodymium iron boron and other ones. So at the border, at the frontiers. So something which is typical from Le Mans, because there were some groups in chemistry very specialized in fluorides. So as you can see, this Fa-F3 is very nice because you have the same chemical composition, but you have 3 different crystalline phases. The rhomboidal one, each TB on pyochlor. Okay? So if you look carefully for the magnetic structure, you can see the first one is a typical antiferromagnet. You can see also the near temperature 363 Kelvin. Then you have the pyochlor, and you can see a decrease of the near temperature. Why? Because as you can see, you have some magnetic frustration. Within the planes, you have hexagons with triangles. And in triangle, antiferromagnetic interactions are frustrated. But in between planes, no frustration because you have only square rings. And finally, the pyrochlore contains only triangle rings. So that means the system is completely frustrated. It's a kind of cagomyelitis. So 20K. So that means that the composition is not a problem, but the structure is very important. So those studies were done in 60s and 70s, and this to show you what about the possibility of Mössbauer spectroscopy. So about above 363K, you have a single line. But this single line is not a pure single line. You have a small quadrupolar splitting. If I remember, 0.08 millimeter per second. That means you have a small breaking of symmetry around iron nucleus. If you decrease the temperature, you will get a nice sextet at 4K. But you are not able to conclude ferro, antiferro, other. Be clear. So, of course, if there is a change, we can look what about the evolution versus temperature very close to the Néel temperature. And you can see that T over Tn 1.0009, 1.9989. That means within a very less than a half degree, you can see a dramatic change of the structure. So that means you are able to determine very accurately the Néel temperature. So that means you need an excellent furnace and an excellent thermometer because you have to stabilize for a long time, at least 5 or 6 hours at exactly the same temperature to get a good Mössbauer spectrum. And you can see that the resolution is perfect. So if you can get many spectra just below the Néel temperature, you can follow the hyperfine field evolution versus temperature, and you can determine some beta critical exponent. And this gives you some information about the magnetic dimensionality if you have a 1D, 2D, or 3D system. So it's quite easy. Let's say that, of course, this sample for the time of registration is very short compared to some other ones. In addition, it was possible to prepare also some amorphous FF3 fluorides. As you can see, up, you have a spectrum of crystalline sample. Below, you have the two spectra. So if you put a single doublet with Laurentian lines, you are not able to reproduce it. Why? You have an amorphous structure. So that means for each iron, you have some typical environment. So you can put 2, 3, 4, 5. The idea is to put a distribution of doublets, distribution of quadrupolar splitting. What you can see is the doublet is perfectly symmetric. That means you have a single value of isomer shift. Single value of isomer shift, that means you have only octahedral units. So that means that the amorphous is composed only of octahedral iron units. Okay, so it is possible to model this kind of distribution. And it was funny because at the same period, the people who was working on metallic glasses, and they gave the same conclusions. So now we have the crystalline sample, as I showed you before, the amorphous one. So you can see it is broadened. The lines are broadened, rather symmetrical. And now we have to apply an external magnetic field. On applying external magnetic field, we have a ferromagnet, as I showed you before. That means you have a distribution of magnetic moments in the block magnetic state. And for this, we were able to develop some modeling by considering an assembly of octahedral units. So, of course, if you consider the rings, you have 3, 4, 5, 6. 3 and 5 frustration of ferromagnetic structure. And this system was a ferromagnet below 29 Kelvin. And the conclusion was to do modeling with dense random packing of octahedral units. On the isomer shift, the value of the amorphous was exactly the same as that for the free crystalline phases. Okay? So now, behavior which is not so common, idle spin. Oh, what is this? The spin is idle. Maybe I am idle also, but... So, at room temperature, you have two doublets. It's clear that we have one doublet typical of iron 2 and one doublet typical of iron 3, according to the value of isomer shift. You decrease the temperature. What you can see is the doublet of iron 2 is still present. And the doublet of iron 3 splits into a sextet. On this sextet, the lines were increasing. That means the hyperfine field will increase when the temperature decreases. But below 20K, you can see that the doublet, the surviving doublet, attributed to iron 2, becomes a sextet. It splits also. Now, if we look carefully, what about the evolution of hyperfine fields? You have, in this case, an evolution here with a small cusp of iron 3. And you have the evolution of hyperfine field of iron 2. And you can see that the near temperature of iron 2 component corresponds to this cusp. Look to the inverse of susceptibility. There is something of the two critical temperature corresponds to the blocking temperature. Why is this? The structure is like this. So that means you have magnetic moments. And so over a certain temperature, you have a magnetic moment. It does not know how to be blocked because there is a kind of competition. And when you decrease the temperature, finally, yes, I can block myself. And why it is idle spin behavior. So now, probably you have studied some systems where you are introducing some substitution to make the system much more simple. And of course, it's possible to do Mössbauer. So, for example, in this case with lanthanum, strontium, nickel, iron, oxygen. And you can see the lines are broadened. But if the lines are broadened, that means you have different environments. Of course, because you are mixing iron, nickel, and maybe strontium and the lanthanum influence. In the case of the sextet, it's the same. So for samarium, iron, silicon. And in this case, what it is possible to use is a binomial distribution. And after, it's possible to describe correctly the different spectra with, I would say, a special attribution of the different components. And to see whether the disorder is homogeneous or not, in both cases. Spin transition. I mentioned that the isomer shift is sensitive to the spin transition. So in the case of iron 2, which is a 3d6, you have two alternatives, high spin, low spin. Okay? So now it's possible to have some systems. So many experiments have been done versus temperature, versus hyperfine field, and also versus light. The idea was to introduce optical fiber within the cryostate and to enlight the sample. And after you can play. So you can see, for example, you have the high spin state, which decreases to get the low spin state. And you have also no light, green light, and so on. So you have plenty of experiments. And it was possible to describe the spin transition phenomena. You have an excellent paper of Philipp Güttlich. I don't know if someone is working with. So to describe all these phenomena. And of course, there was also some DFT calculation to support the different results. So as I mentioned this morning, so we can see sometimes the doublet, the intensities of lines are different. So of course, it was a sample of clinochlor, so for geologists. So at the beginning, the temptation is to put only doublets with same intensities. But it seems that if you can fit perfectly the spectrum, you will obtain some components, the isomer shift of which has no physical meaning. So what to do? So as you can see, You have money. If you put money over a substrate, it's difficult to have all coins oriented with the same direction. That means you will get a distribution, which is the same case in some minerals, which exhibit some layered structure with three octahedral structures, and typically of clays. So in this case, what we have to do is to check about the texture effect. And there is a solution to rotate the sample at the magic angle. By rotating the sample, we have the same sample, but different spectrum, except that the angle of the gamma beam differs from that of the classical one. And you can see that now it's possible to describe the spectrum with doublets, with Lorentzian lines, with same intensities. So that means that it's very important in some cases to check what about the origin of the difference, the intensity difference between the two lines. Okay? So some application in geology. Also, I can discuss a bit about the problem of samples in geology, because when you are studying some, I don't know, some perovskites prepared at the lab, so you have maybe 200 milligrams, maybe more, it's very homogeneous. But when you want to study some soils, so once a geologist from the University of Le Mans came to me, and I want to check what about evolution of such parameter, because there was a river which was expected to go in this way. Now it is in this way. And he was studying. But please, in my case, I need 100 milligrams. In your case, you will use maybe tens or hundreds of tons of sample. So how to do? So the problem was for me, because no problem. I have distinguished 5 different zones. I will give you 10 samples for each one. Thank you, because now I have 50 spectra to perform. Okay, nevertheless, it was very interesting because all spectra for one zone were exactly similar. And of course, they were different from one zone to another zone. That means that his sampling was perfect. And it was after possible to distinguish about the different components. So now you have such a spectrum, which is very strange. Whoa. Sextet, doublet, not know. But maybe there is some nano grains. So without using money, without using cryomagnet, we can apply a small magnet, and it was possible to see a strict change of the hyperfine structure. Of course, we cannot see completely sextet because the field developed by the magnet was not enough. But it was possible to see sextet and doublet. So there is some superparametism effect. So that means that progressively we were going back. So as I mentioned this morning, amorphous magnets, but glasses, obtained in the 70s. It was following the experiment of Paul Duvez in Caltech. So the ribbons typically are between 25 and 35 micrometers when they were obtaining by melt spinning rotating wheel. Sometimes it is possible also to obtain wires using in-row wasps. So that means the wires are not so homogeneous and they are thicker. So the characteristic is a single crystallization peak. You are from the amorphous, you go to the microcrystalline state, and it is not reversible, of course. So interesting for the magnetic and the mechanical properties. So now the spectrum, broaden lines. So for the sextets, as well as for the doublets. So again, a problem of strategy, how to fit spectra with broaden lines. So we develop some strategy because here, what we can see that maybe we have for this spectrum 3 to 1, but it's still possible to fit. And I remember it was during my first thesis, and of course, I have checked what about the amplitude of the hyperfine field distribution, about the influence of radipolar shift, the influence of isomer shift, or the intensities of the second line. And finally, we concluded that, of course, it's possible to get a spectrum, free texture spectrum, by rotating the sample with the magic angle. Because during the quenching, finally, you will get some orientation of magnetic domains. It's according to the cooling of the system. So that means here, for example, you can see, so as quenched, you apply an external magnetic field, you have, I would say, 3 for 1, and after, with the magic angle, you have 3 to 1, and you can combine, and you will obtain what about the mean value of the angle. And that means you can relate with the physics of the system. So at the end of the 80s, Yoshizawa and his group in Japan, they were finding a new family of systems, so which have been called nanocrystalline alloys. So typically, maybe if you heard about fine met, nanoperm, heat perm. So the main characteristics, they present 2 crystallization peaks. After the first one, you will get some nanocrystalline grains embedded in an amorphous matrix. So as you can see there, a series of spectra. So you can see the pure sextet after heating at 450 Celsius. Without crystallization, you will see a change of the intermediate line. Why? Because you are relaxing the internal stresses. And by relaxing the internal stresses, because such systems are magnetostructive, you will also change the orientation of the magnetic moments. So you will a kind of rotation, either within the plane to out of the plane or out of the plane into the plane. It depends on the positivity or negativity of magnetostructure. And after, at a higher temperature, you will see the appearance of a small sextet. And after it is increasing. Of course, you have some grains, crystalline grains, embedded in the matrix. So we made, and it seems to me that we were the only group in the world to make some experiments from low temperature up to high temperature to get a pure analysis of all the Mössbauer spectra. So if you will look carefully, it's difficult to fit the spectra by only 2 components. It is necessary to introduce 3 components. And of course, what it was able to consider that we have the amorphous matrix, reminder, so with disorder, and it is by red atoms. We have the crystalline grains by yellow one, and we have the interface. And the interface plays an important role because you have the black atoms. They correspond to some molybdenum or zirconium, which create a kind of wall to prevent the growth of nanograins. So it was perfectly possible to describe only by 3 components. And by doing some in-field Mössbauer experiments, it was possible to see that you have ferromagnetic grains, you have the ferromagnetic matrix, but you have not ferromagnetic interfaces. They have a kind of spin glass-like behavior because the magnetic moments are totally disordered. Okay, so it is possible to correlate with magnetic measurements. It is possible also to discuss about the systems which contain a low content of nanograins. So when you are at high temperature, nanograins are rather far, they cannot interact. So you have some fluctuation. They are superparamagnetic. But when you increase the number of nanograins, they will interact because they are rather close each other. In addition, what you can see is that the amorphous matrix is not perfectly paramagnetic because you will create a polarization of magnetic moments of the matrix through those of grains. And it is not possible to observe by other techniques. And we made also some computer modeling to check about the presence and the thickness of this grain boundary. And the grain boundary we obtained was exactly the same order of the grain boundary observed by Monte Carlo simulation. And we have also different cases here. And this was able to provide us information. Low temperature strong interaction, magnetic interaction within the amorphous matrix, within the grains, and strong interaction between grains and amorphous matrix. When you increase the temperature, you will reduce the interaction within the amorphous grains, which progressively becomes paramagnetic, completely or not. But what is important is that the cohesive field will be zero when you have some supermagnetic behavior of the crystalline grains. Other case. So there were a lot of studies about ball milling of alloys. So sometimes it was possible, we have seen some paper with ball milling of aluminium, iron, chromium, boron, silicon, manganese. So maybe there was too many atoms. So we limited, in our case, to iron, which is a bit complex. So we made some X-ray diffraction, and the X-ray patterns were described by means of two components, better said, by three components. No, yes, three components because we have a background. But the two main components, the physical components, were corresponding to crystalline grain on something which was rather disorder in between grains. In addition, it was possible to conclude that the grains were rather cubic. So now you have to pile different cubes on in between, but you have the grain boundaries. Okay? Doing Mössbauer spectra, no changes. Oh, very strange. And of course, it could be possible to see some changes by increasing the temperature. But if we increase the temperature, we could also modify the nanostructure. So it was a problem. And by decreasing the temperature, no changes. So from X-ray diffraction, it was possible to estimate both components. And from field cool, zero field cool measurements, so yes, there was grain boundaries. So since by Mössbauer, no grain boundaries. Okay. So this result was different from that of the group of R in Hull, where it was possible to see different components, but the structure was also totally different. So we used a computer, and the idea was to push a few blocks in order to get a minimum of energy. And the main characteristics of at the end were the nanostructure. The size of the grains were rather similar to that observed by Mössbauer, because it was possible to estimate finally the content of grains by X-ray diffraction, the size, and finally the thickness of the grain boundaries. And the thickness was experimentally 0.08 nanometers, and by computer modeling between 0.7 and 1 nanometer. So the results were very consistent. And the main conclusion also was that there was no FCC phase, as it was predicted by other groups. And now it was possible to explain that the small differences between the structure within the grain boundaries on the grain could explain that it was difficult to see a difference, two components in the Mössbauer spectra. Okay, we have done also with iron nickel. So to check what about the INVAR transition. And of course, X-ray diffraction, we could distinguish PCC and FCC. And in the case of Mössbauer, it was possible, but it was difficult to fit all spectra. We had to develop some model. And the model, as you can see, an extension is there. And you can see that we can repeat also, we can observe again the INVAR transition in this system prepared by ball milling. What it was very funny is once I was in Tunisia, and someone was working also with iron nickel. I had obtained a few spectra, and I applied directly this model, and all spectra were fitted within 5 minutes, because the model was prepared before for other situation. So I come back to the fluorides. So the idea now, I was asking several times to the colleagues, please, could you prepare nanoparticles of iron of Fe3? But they were not able. Maybe I don't know if they were very motivated. But in addition, the problem of iron fluorides, they are not stable in air. So Nevertheless, we have prepared by ball milling, and the idea was to store the system in glove box, to prepare samples in glove box to avoid some evolution of the sample. It was rather successful. X-ray diffraction, also the same. The powder was under a kind of dome to protect from atmosphere. So two components, one component attributed to the grains, and another one attributed to grain boundaries. From NMR, so we did not perform NMR on iron iron F3 because, of course, of the dipolar magnetic interaction, but we use gallium F3. Gallium has the same size as, gallium 3+, the same size as iron 3+. Now, the main problem was that at the beginning here, we have rather 50-50 or 40-60. But as you can see, for gallium, there was a large contribution of grain boundaries. So the problem now is to read what about the information. When you are playing with nanostructured powders, so what is the limit for X-ray diffraction? What is the limit for a local probe technique? And of course, if you look, for example, here, so this component, green colored, belongs to the grain when you are considering X-ray diffraction. But when you are considering some local probe technique, this component belongs to the grain boundary because there was some distortion. Here it is a schematic view. So finally, by considering this layer, it was possible to obtain the same quantity for grain boundaries, 43%, 45%. And of course, we perform Mössbauer. Mössbauer at different temperatures. So here we can see that there is 2 or 3 components, one attributed to the grain, one attributed to the amorphous, which can be assimilated to grain boundary, and in addition, a third one in between that corresponds to the green one. We applied also an external field, and it is possible to see that the decomposition is the sextet, the blue sextet, typical of antiferromagnetic structure, and the red component, the green component up, corresponding to ferromagnetic structure. So, from this, it is possible to discuss about the schematic view. So, we have the evolution of the bulk FAF3. We have the evolution of the crystalline, of the hyperfine field of the crystalline grains, which is a bit lower, probably due to some superparametric relaxation phenomena. We have the amorphous, which goes down to 29 Kelvin, and we have the contribution of grain boundaries. So why? So if we look carefully, at low temperature, we have, as I mentioned, everything is blocked. Grains on amorphous boundaries. Up, everything is paramagnetic, but in between, you have the influence of the grains over the amorphous situation. And it's possible to have a kind of exchange bias phenomena in between. So the transition between spero and para has to be accompanied because you have static and dynamic phenomena. And by considering here the evolution of the coercive field, you can see that you can estimate the blocking temperature when the grain boundaries are very thin. You have a blocking temperature equivalent to the Néel temperature. That means you have no strong dynamics, but when the grain boundaries are rather thick, of course, you are preventing interaction between grains. That means you have a blocking temperature which is lower than the Néel temperature. So, computer to make structures, okay, boom, with the 2 structures. So we have to maintain the structure was containing about 30,000 atoms with 3 times more atoms of fluorine than iron. And now looking what about the structures here on the magnetic structure. And it was possible here to find a disordered magnetic structure for the orientation, consistent with the ferromagnetic behavior as observed here by in-field Mössbauer spectroscopy. So now For spinel, Nader will complete this afternoon, but I have a few things to show you. So the interest to apply Mössbauer, the interest to know when you are working with spinels, whether they are either they are micro or nano. What about the cationic distribution? Because it will give you the magnetic behavior. And of course, you may have magnetic frustration, spin glass-like, cationic inversion, reverse spins. So you have plenty of different situations. As I mentioned before, in the case of micro, as well as in the case of nano, ferrite. Of course, in the case of nano, you have to add the contribution of surface. So now the big problem of magnetite, nanoparticles, because everyone during 20 years were doing nanomagnetite, but finally, are they nanomagnetite? The typical spectrum of nanomagnetite is like this. So you have two main components at room temperature. That means above the Vervet transition, and which is 119 Kelvin. So you can distinguish easily iron 2 plus, iron 3 plus, sorry. The second component, it's not iron 2, it's not iron 3. But if you consider the values of isomer shift, it's just in between. That means above the Vervet transition, you have, as observed by Mössbauer, you have 2.5. That means it's possible to cut electrons in two parts. Really to see some phenomena of delocalization. So now, if you have some nanoparticles of, let's say, magnetite, what you can see is that you have also two components. But if you see carefully, the outer component is larger than the inner components. So if you look carefully now, the mean value of the isomer shift, it is decreasing. That means there is a tendency from something iron 3 plus plus iron 2.5 to iron 3 plus. That means there is some oxidation. And of course, the surface might be oxidized. If the surface might be oxidized, so you will have a transformation of Fe3O4 in gamma Fe2O3, magemite. And it's possible to estimate the thickness of this layer. And finally, if you have very small nanoparticles of nanomagnetite, finally, it's not magnetite, it's magemite, because the thickness is about 3-4 nanometer thick. So now you apply an external magnetic field, and of course, at 0 Tesla, at low temperature, no result structure. But if you go up, according to what I explained this morning, so we have a splitting. So it's possible to estimate tetra and octa. In this case, it corresponds to magemite. So now you consider nanoparticles of different sizes. The diameter is given on the left side. So you can see from 2.7 up to 10. So prepared by Jean-Pierre Jolivet, as Davide mentioned this morning. He was a chemist. And after we made some experiments, such nanoparticles were far enough to prevent any interaction in between. So they are free. So what you can see that you have a decrease of this line. So progressively we arrive to 301. So that means you have a change. But what we can consider is that over 10 nanometers, the surface is not the same. The contribution is not the same. So it was possible to describe by means of a ferrimagnetic core with a random distribution of magnetic moment at the surface. And it was possible to estimate that the magnetic surface about 0.7 nanometers, let's say about 2 atomic layers. And this result is very important because Nader will explain this afternoon that, of course, these two layers are very important at the interface. So, sorry. So now the idea was to introduce nanowires in nanotubes. So it was quite successful. On the same, it was possible to see that the in-field Mössbauer spectra was able to solve the solution in the sense that you have a packing of nanowires, and you have a tendency to have a spin glass behavior, spin glass-like behavior. That explains that the lines here are not well aligned, are not equal to 0. So for application in for medical application, sometimes to graft some molecules. So at room temperature, the spectra was not so easy to fit. At 77K, you can see that in presence of dopamine, the up spectrum, there is a third component, which is green colored. Okay? So the third component, you can see here, its presence. For the as prepared, no problem, as expected. But for the dopamine grafted system, so you can see those two first components or the third one. Isomer shift is a bit higher. That means you have electron transfer. Then you can see that there is a decrease of one component much more than the other one. In fact, it indicates that the dopamine will be sit on octahedral sites, not on tetrahedral sites. Okay, so by DFT, it was possible to confirm these different results. I am close to the end. So now, as I mentioned, Nader will discuss this afternoon on other systems. So, but now there is a kind of zoology for nanoparticles. You can see a core shell, embedded, raspberry, hetero, and so on and so on. So I have studied many of them. And of course, by using Mössbauer at different temperatures, and in addition, apply external magnetic field, it's possible to get very interesting information. So here, for example, the growth of particles. And of course, because the question is, you have a germ, it is growing, and then it is oxidizing. Or you have a germ, it is oxidizing, and then it is growing. So what is the solution? It was possible to, by considering many studies, not exclusively Mössbauer, to have some information why you have, for example, spheres, cubes, platelets, or stars. Here, it was another concept is to create anion structures. So we have a nanoparticle, we will recover per one layer, we will recover by another layer, and we will follow the evolution of the magnetic structure on the magnetic surface anisotropy. So you have some references. Okay, so to apply, for example, other topic. So in this case, it is some canister which were used in some nuclear power plants, and to see what about the evolution. And of course, the main problem was to make samples. So the idea, it is given here for the distance. So now we are not with nanometers, but we have millimeters. And I made a spectra, all spectra. And after it was possible from the evolution of the hyperfine structure to understand what about the different phenomena with diffusion. So the same by doing some reaction on the magnetite for soils. So that means that to test about, for example, the pollution, the idea is to go now with arsenic and to go with cadmium to see what about the processes of reaction on nanograins or nanoparticles of magnemite. So conclusion. So as you have, or as you have concluded maybe by yourself, so preliminary point to have good samples, whatever they are. To have possibility to reproduce the sample. To have homogeneous ones. If they are not homogeneous, Mössbauer will tell you, it's not perfect. Okay? That means that you have to collaborate with excellent chemists. So it's the second conclusion for me. Requirement. So of course, it's necessary to have many experiments, not only from Mössbauer, but in the case of Mössbauer, to have studies versus temperature, to have studies versus external field. maybe other stimuli. So as Nader will show you this afternoon, so we spent 1 year to fit one spectrum to get the right model. We spent also a long time to fit spectra obtained on some hollow nanoparticles prepared by Mr. Pedis. Yeah. So each time you cannot say we have a model which was working for other system. You have to think again, the fitting model is the same, but you have to adapt to the main system, to the new system. So that takes time, and you have to discuss, of course, with chemists, and to compare with other results. So conclusion about Mössbauer, non-invasive, non-destructive technique. It can be useful in chemistry, in physics, in biology, as you have seen, Earth, on Mars, archaeology, and so on. You need small quantity of samples, typically 15 milligrams of iron. I did not change because our samples are p square centimeter. No reason. So powders, thin films, multi-layers, frozen solution, and there is also a possibility to dope with iron. But the problem, of course, when you dope, where is locating the doping element? So you change, but you have to ask new question. Atmosphere. So you have to consider the history of the system, the stability, the aging, for example, in corrosive systems. What about the history in order to conclude? So the tendency is now to do some in situ and sometimes in operando experiments. For example, in the case of system which is system in relation with energy, charge, discharge. So with a group in Montpellier, they developed a lot of experiments. So instrumental facilities, furnace, cryofurnace, cryomagnet, devices, and so on. I would say a single spectrum is still frustrating, because sometimes you cannot conclude. So you need to have further experiment. Modeling facilities, so it could take time. So you need plenty of other measurements. So what is also important is to play with computers in order to compare. With DFT, it's possible to calculate isomer shift, to have ideas on the hyperfine field, on the structures. So then it's possible to have some communication between these results and the results obtained by Mössbauer. So the future is, of course, synchrotron. Oh, now I think I have to acknowledge, as you can see, there is plenty of French colleagues. So most of them belong to a laboratory of chemistry, of different chemistry, other ones of environment science, and for different countries, as you can see. Thank you for them, and thank you also for your attention.
So, thank you, Jean-Marc. Thank you very much. I guess that we are a bit over time. So, no, because there is Nader now. You don't want to let him talk, I guess. No, I guess it is now. But I guess that we have a long lunch break, and then you can really jump to Jean-Marc and make a lot of questions. Just to want to clarify something that is probably important, the idea of this workshop. So let's say really thanks to Jean-Marc, because you have more than 2-hour lectures introducing, first of all, the, let's say, basic of Mössbauer. But I didn't say at the beginning, Jean-Marc is co-author of almost 700 papers. It means that he covered more or less all the aspects of Mössbauer. Then what I want to transmit people, especially from local people from UNIGE, is that you can find some application for Mössbauer for sure in any kind of let's say, field. We have geologists, we have biologists, we have even engineers a lot, and this is quite important. Last comment about samples, of course. To produce, we are chemists, to produce good samples is really tough. That's the main problem. This is the main problem. And most of all, to be sure about the samples. And this is quite tricky, and so my guys knows very well because they are spending a lot of time in doing this. This is quite, of course.
Once I had discussing with some colleague during a conference. Let's say I have a perfect sample. By discussing, progressively the sample was not so perfect. And after I made a Mössbauer spectrum, it was not perfect. The problem is not to do some non-perfect sample. It's also to help people. So I am sorry, but I cannot obtain this one. So you will obtain this. So how to improve? Because what you will obtain can bring information how to improve the chemistry. And definitively, especially with people from Strasbourg, we were discussing quite often. Sorry, Nader. So once they were expecting to prepare some nanoparticles using some stearat, iron 2 and iron 3. Okay. But the results were the same. So suddenly, I asked them, please send me the sample of iron 3 stearat and iron 2 stearat cell from the company. They were similar. So in the iron 2, there were no iron 2. So you have also to be very careful on this. But by this way, it was not aggressivity. Please send me. So it was good for both of us.
I totally agree. Then let's say thanks again to Jean-Marc Greneche for the nice talk. So now I will leave the chairing of the session to Pierfrancesco Maltoni, that will introduce the second invited speaker of today. 30 minutes total.
Okay, thank you. So now we can welcome Professor Nader Yacoub from Le Mans University. Nader has had a lot of expertise in Mössbauer spectroscopy, and today is going to give us a nice talk about oxide nanostructures.
Okay, thank you, Pierre, and I would like to thank Davide and Sausan for their invitation. So it's a great pleasure for me to be here today. I will continue the discussion about the contribution of Mössbauer spectrometry on the study of magnetic nanostructure structures based on iron. So in general, magnetic nanostructures have a significant potential application and for application in for nanotechnology, storage transformation, nanomedicine, biotechnology, and other many fields. And their performance depends strongly on the relaxation time, which is depends on the structure, the shape, the morphology, the nano composition of these nanostructures. Their physical properties are governed by the field size effect, quantum confinement effect, because the large number of surface atoms and that allow to the presence of different mechanisms like exchange interactions, spin disorder, dipolar interactions, or collective behavior. So we need to study these properties in order to understand their physical properties and control their potential for applications. Among these nanostructures, the spinel structure is a very rich system because the correlation between the spin structure, Casimir distribution, and general physical properties. And after, if we, by introducing a new phase, magnetic phase like antiferromagnetic phase or another phase, and by changing the morphology, we obtain more complex structures like core shell or hollow and nanocomposite. Jean-Marc presented previously the system of nanohybrid. Also, it is a very interesting system for application of biomedical. So this complex architecture allows the presence of different mechanisms, interfacial mechanisms like exchange bias, like big spin disorder because the surface effect, and something like spinning magnet coupling or exchange coupling at the interface between different ferrites. So Okay, in this domain, Mössbauer spectrometry is very powerful technique as local probe technique, and especially in field Mössbauer spectrometry, as presented by Jean-Marc previously. So by applying external applied field, we are allowed to splitting the two subspectra and have a quantitative information about each iron sites. And okay, from this we obtain the information about hyperfine field, but also the information about spin structure from the spin counting. And for more complex structures, we need to find the appropriate correlation between the effective field and the correlation of the spin counting in order to obtain the correlation, the distribution of the hyperfine field. So for the next, I will present one example of each system presented. I start from cobalt ferrite. Then I present an example about core shell of iron oxide and monoxide of cobalt. Then I will speak about the ultra-thin hollow nanoparticles. And finally, I present a recent study about nanocomposite of strontium hexaferrite and cobalt ferrite. So the idea is I will progressively increase the complexity of the structure, starting from simple magnetic phase to nanoferrite with well-defined interface in order to show the relevant parameters that we could obtain from Mössbauer spectrometry. Okay, spinel structures was presented by Jean-Marc. Here I will just for example, for the iron oxide, for different cobalt spinel structures, the exchange interaction between ions, type super exchange, it is indirect exchange interaction, type super exchange or double exchange, the exchange integral between ions depends strongly on the nature of the atoms A and B, but also the positions of the atom A and B in the sites, and the angles of super exchange. That's mean change any parameter between these parameters allow to the new physical properties. Donc for that, it's a very rich system for study and for application. So a comparative study between two cobalt ferrite prepared by two different chemical syntheses. The first obtained in polyol and the second obtained by thermal decomposition. The crystallographic structure showed by XRD, they have the similar spinel structure, the similar crystallographic structure, but also they have a similar size. So now if we see the magnetic measurement for the magnetic particle prepared by thermal decomposition, we obtain a very high magnetization saturation. So a mass are rather close to the bulk values. And we obtain also a very high coercive field. So what is the difference between this behavior of the similar magnetic nanoparticles? For that, we applied external applied field. We performed the measurement under external applied field, and we obtained these two spectra. The first one is a classical spectrum under field. We observe a splitting between the two subspectra for A and B with narrow line and with very small intensity for the intermediate lines that show a very small spin counting. But in the case of the magnetic nanoparticles prepared by thermal decomposition, we obtain a spectrum with more complex hyperfine structures. So the spectrum here is characterized by a broadening line with some overlapping, but also with large intensity of the intermediate lines, order 5 and order 2. So this spectrum normally we need to find the appropriate correlation between the distribution of the effective field for each subspectra correlated with the distribution of the spin counting in order to have the information about the hyperfine field. So by doing that, we obtain the distribution of the hyperfine field, and we do the correlation between the distribution of the hyperfield and the spin counting are related to the cation distribution. So the position of the iron 3+ ion in B and A side with nearest neighbors of cobalt 2+ in A and B sides. And that allows us to have a mean schematic representation of the magnetic environment of iron located in A and B. And from that, started from that and from the local magnetic moment obtained from the Mössbauer spectrometry, we arrived to reproduce the high magnetization at saturation observed by SQUID. And so the Cassini distribution and the correlation between Cassini distribution and the spin canting allow us to understand the macroscopic properties, magnetic properties in this kind of cobalt ferrites. So now if we introduce a new magnetic phase on oxide, like antiferromagnetic phase, for example, on iron oxide, cobalt ferrite, anything but ferrite, ferrimagnetic or ferromagnetic with antiferromagnetic structure. Donc the core shell structures is very interesting system because the interface effect allow us to have exchange bias coupling. So the problem is the big coercive field observed in zero field cooling mode. So what is the physical origin of this coercive field? We performed the Mössbauer spectrometry at different temperature, and different spectra show a complex hyperfine structures. For example, at room temperature, we observe a mixing between doublets and sextets with a Browning line. So the mixing between blocked and unblocked magnetic moment. And for the sextets line, we observe some similarities with magnetite presented by, for example, by Jean-Marc previously, but we don't observe the same percent of octa and tetrahedral site. As first, we can guess that our structure is formed on magnetite and surrounded by magemite. Now the measurement under, at 77 Kelvin, Jacques sextets remain present in here. Normally for the magnetite, we have a model forming with 5 subspectra, the model with 5 components. We arrived to reproduce the experimental spectra correctly using the 5 subspectra of iron oxide, but the hyperfine parameters obtained here are different from those expected for a stoichiometric magnetite. So now, in order to have more information, quantitative information, we applied an external field. And okay, the spectrum for the site subspectra A is classical, so it's characterized by a narrow line. We can reproduce this subspectra easily using one subspectrum. But for the subspectra of site B is more complex with complex hyperfine structures. So the shape is typical corresponding to magnetite, but because the presence of iron 2+, but using the 5 models of magnetite, it's not possible to reproduce correctly this subspectrum. So we need to add a new subspectra of iron 2+. So the hyperfine parameters for this subspectrum are different from the hyperfine parameters of the iron 2+ of the magnetite. So the description shows the presence of supplementary component of iron 2+ in the structure. But if we see the hyperfine parameter of site A and B, we observe that the hyperfine parameters of hyperfine field are bigger than to those of iron oxides. That's mean we have a mixture of magemite, magnetite, okay, but also we observe a diffusion of cobalt, allow to a formation of a new magnetic phase type cobalt ferrite with the presence of iron 2+. So we can guess core shell structures that allow to understand the high coercive field observed by SQUID. So now if we change the morphology of the magnetic nanoparticles, the hollow magnetic nanoparticles is an ideal system to study the surface effect because the presence of extra surface layers. So we have more pronounced surface effect and more importance of surface entropy. So in magnetic nanostructure, the understanding the contribution of surface entropy and surface effect on the physical properties is not well understood. Any unexpected behavior, we attribute that to surface effect. But this system is formed just from the external and internal surface, and we hope that we arrive to understand the physical properties and the contribution of the surface effect in this system. So the obtained hollow magnet nanoparticles is characterized by a very small thickness. And if we compare the surface to volume ratio, we found that R is bigger than R found in literature. So we have a lot of surface in this system. Now, the measurement, the magnetic measurement on these nanoparticles show a very important shift, a horizontal shift in the isotope in mode field cooling, but also vertical shift. So this behavior is typical for the presence of the exchange bias coupling. So the question is that, as explained, the exchange bias coupling results from the exchange interactions between the interface at the different magnetic phases. But here just we have one magnetic phase, so iron oxide. So what is the origin of this shift? For that we performed the Mössbauer spectrometry. At room temperature, we obtain doublets, slightly asymmetrical. It's not seen, but it's slightly asymmetrical, and characterized by Browning line with no Lorentzian lines, so typical for amorphous structure. And to reproduce this spectrum, we need to correlate the distribution of the isomer shift with the distribution of quadrupolar separation. The fit is very well, and we obtain the parameter Q, parameter quantifying the topological disorder in the case of amorphous. And the obtained value is totally different from the value of the amorphous state. So the structure is not amorphous, but also it is not crystalline. So we have something like polynanocrystalline structures. So the measurement under without external field at low temperature show the presence of sextet with some Browning line, but very overlapping line, and asymmetrical lines corresponding to the presence of A and B side in these structures. So from that we can't obtain any quantitative information. Now we applied an external applied field. So the obtained spectrum is very complex, as not consistent with the usual ferrimagnetic structure as presented previously. So the spectrum is characterized by a very Browning lines for each side, but also large intensity of intermediate lines. So this kind of hyperfine structures, we need to do the correlation of the effective field with spin counting in order to obtain the hyperfine field. So we fit that using two different methods. The first method, we introduce two subspectra corresponding to A and B side, but using a Gaussian line. So that allows us to have directly the mean information about hyperfine parameters. So the fit is okay, but it is not physical because Mössbauer line is a Lorentzian line. So now, starting from the mean information obtained here, we can do the distribution of the effective field with the spin counting in each side, and we obtain some correlation. And from that, we obtain the distribution of the hyperfine field. So the most important information here is the large Browning distribution of the spin counting. It covers all the space from 0 to 90. That means we have the spin in all the directions. So from this fit, it's okay. We arrive to fit the spectrum. But if we can see the shape of this spectrum is not so different to the theoretical spectrum under field of the spheromagnetic behavior. So spheromagnetic, as presented by Jean-Marc, is an exotic magnetic order observed usually in amorphous or disordered materials, where the atomic spin are frozen in random orientation. So each spin has a specific magnetic entropy. But we have some difference in the external lines here and here relatively to our experimental spectrum. So we have the inverse of the order of the intensity. For that, it is not possible to reproduce these experimental spectrum using just one subspectrum corresponding to the ferromagnetic structures. We arrived to reproduce this spectrum using two subspectra corresponding to two ferromagnetic-like structures. Okay, so with opposite hyperfine fields. So we have something of two ferromagnetic, antiferromagnetically coupled. Now, also we have interesting information from here. The proportion of octaside are much larger than expected in case of the iron oxide. And because these questions, it was observed, there was some tendency of the surface are closed by more octahedral site than tetrahedral site, but it is not possible to prove that directly from experimental measurement. Now, for this system formed just from the surface, we have done the experimental proof of that. Okay, the fitting model is okay, work well. We arrived to reproduce the experimental spectrum, but there are some difference between model here and experimental. Here model and experimental and model, but that we arrived to reproduce this difference easily by introducing a new minor subspectra corresponding just to ferrite, ordered ferrite. So finally, we can we modelize our structures as 3 layers, 2 disordered surface layers separated by one layer with a certain order of spins. So the exchange between the spin at the interface of the 3-layer system allow to the presence of this exchange bias coupling in these materials. So I try to go quickly. Now, the last system I present is the recent study obtained on ferrite heterostructures, strontium hexaferrite and cobalt ferrite. So that's the discussion on this section. Normally will be continued by Samuel in this afternoon. He will do the correlation between the Mössbauer measurement and zero NMR measurement, maybe other properties from other techniques. So it's an interesting system because it is an alternative for permanent magnet. So it is interesting for rare earth free permanent magnet because in the hard, soft nanoferrite, we have the possibility to have exchange interactions, interfacial exchange interactions, or spring magnet coupling. So we can that allow maybe to perform a permanent magnet without rare earth material. Strontium hexagonal, the hexagonal structure, strontium hexaferrite, in the hexagonal structure of strontium hexaferrite, we have 5 sites of iron, an equivalent site of irons distributed in 3 octahedral sites and 1 tetrahedral site and 1 trigonal pyramidal site. So the configuration of this spin is presented here. So this material is a hard material and characterized by a strong magnetic anisotropy. And cobalt ferrite, he has a spinel structure as presented previously. And also is a semi-hard magnetic material and characterized by strong magnetic anisotropy. Now I present the Mössbauer spectrum for strontium hexaferrite for a pure strontium hexaferrite at room temperature. We observe some overlapping, but we have the site 12K and the site 2B are well resolved at this temperature. But because the overlapping here also, it's not a problem to reproduce correctly the spectrum using the 5 subspectra corresponding to 5 sites of strontium hexaferrite, and the obtained percent of each site corresponding to the theoretical value. And that because we have a correlation between the hyperfine field, quadrupolar shift, and isomer shift for each site. also we performed the measure at 77 Kelvin, but at 77 Kelvin, we observe a net increasing of the hyperfine field, of the value of the hyperfine field of 212 side, and we observe more overlapping. So better, the discussion is better at room temperature. For the pure cobalt ferrite, we observe just the presence of sextets with overlapping, asymmetrical but overlapping. So from that, just to obtain the mean information, indicating the presence of two octahedral and tetrahedral site, and correspond to a blocked magnetic moment. So for the nano composite of strontium hexaferrite and cobalt ferrite, okay, the spectrum at room temperature is not so different from the spectrum for pure strontium hexaferrite. But here, normally we expect 7 sites. So 5 sites, 5 subspectra from strontium hexaferrite and 2 from cobalt ferrite. But the hyperfine parameters of octahedral, tetrahedral site of cobalt ferrite are not so different from the hyperfine parameters of octahedral and tetrahedral site in the case of strontium hexaferrite. For that, I obtained directly the mean information for the mode is enough to have a qualitative description, because we observe some changing in different hyperfine parameters, but it's a qualitative description. But for the site of 12K, we observe some Browning lines. So it's not possible to reproduce the 12K using just one spectrum for 12K. We have to add additional subspectrum, and so we observe an emergence of a sixth spectral component. So the hyperfine parameter of this subspectrum is between the hyperfine parameter of 12K of strontium hexaferrite and the octatetra for cobalt ferrite. So for that, we attributed this subspectrum to the iron 3+ ions located at the interfacial octahedral site shared between SFO and CFO. And that's possible. Why? Because from crystallographic structure and transmission electron microscopy, we observe a very well-defined interface between strontium hexaferrite and cobalt ferrite. So we have some epitaxial growth of CFO on SFO. And this tendency was confirmed for different proportion of strontium hexaferrite and cobalt ferrite, 70, 30, 50, 50. We observe the presence of this additional subspectrum. Now, in order to confirm this hypothesis, we performed a measurement on a physical mixing strontium hexaferrite and cobalt ferrite. Normally, in this case, we don't have an interface, and the Mössbauer spectrum at room temperature show, okay, it is a classical Mössbauer spectrum for strontium hexaferrite. And here the site corresponding to the 12K is characterized by a very narrow line. So using just one subspectra, it's possible to reproduce this subspectrum. But we observe the presence of doublets. I think these doublets became from some isolated magnetic nanoparticle of ferrite, because we mixing the cobalt ferrite with strontium hexaferrite. Maybe we isolate some very small size particle with very small size, and they have a super paramagnetic behavior. So as I said, the discussion, I finish. The discussion on this section will be continued by Samuel in this afternoon. So at the end, I conclude with a general conclusion. It's clear, in order to understand the physical properties of magnetic nanostructure with complex architecture, we need to elaborate a strategy based on multimodal characterization, based on the correlation between local probe technique, Mössbauer, NMR, neutron diffraction, and others, with the macroscopic technique and also numerical simulation. It's important in order to understand their physical properties. And finally, I would like to thank all the collaborators involved in this study, and especially Professor Davide and his research group, because the most of examples presented here were studied in collaboration with Davide. And thank you for attention.
So, thank you a lot for the presentation. It was very interesting. I guess that all the audience had a very good showcase of what we can do with Mössbauer spectroscopy, moving from the molecular structures that Jean-Marc presented before and now with Nader. So there will be more in the afternoon, but you have some special questions for Nader. Maybe we can have it one now and later after lunch.
Just a comment, Nader. Of course, thanks a lot for the nice presentation. I'm really happy that we are here. We are working together for many, many years now. And so, but just about the paper of cobalt ferrite that you presented at the beginning, that actually is quite well-cited paper. Of course, it was constrained for the time, but I would like to mention that this paper was involved even other person from Genova. And it was very interesting because I guess that is, Jean-Marc, maybe you can confirm, one of the first paper in which we compare neutron diffraction with Mössbauer spectroscopy. And we got exactly the same value of cationic distribution. This was very interesting point. We did this job with Alberto Martinelli and Maurizio Ferretti in Grenoble, and it was very interesting. Just this comment. Thanks again, Nader.
Okay. About this one, so it was the first for me. It was the first collaboration with Davide from I don't know now 15, 16, 17, 20 years. So this is the spectrum mentioned by Jean-Marc. Needed 1 year in order to arrive to have this the fitting. So the fitting presenting here, okay, we can see is easily we have some correlation. But the problem we have some overlapping. So we need normally another technique, use the inversion decree obtained from neutron diffraction, and the mean magnetic moment directly obtained by neutron diffraction. Use it here on the distribution in order to obtain the magnetic at saturation at low temperature. So it was like a ping pong during 1 year between the different technique to arrive to this conclusion.
The main problem of these samples is that Alberto want 2 grams, so 1 gram to do neutron diffraction. And for this reason, we need to do self-combustion. That is not the most controlled synthesis, as Pierre known very. But it was the only synthesis method that allow us to do this comparison. And this paper, it's after 15 years, is still really, really well cited. Sorry, Jean-Marc.
Also to add that finally we have very small nanoparticles, and to conclude that they are not chemically homogeneous. So it's very important because sometimes we have some results which are a bit special. So we have to think if the structure is homogeneous. So it's very important for this. And what I wanted also to add is respect to the hollow nanoparticles. So finally, we were discussing 25 years ago with Jean-Louis, with Dino, and with Elisabeth Tron, what could be the surface of nanoparticles, especially of magmite. And we have the conclusion that probably there is much more octahedral units yet than tetrahedral units. But we did not get any argument. It was only assumption. Why not? But and now, thanks to these measurements on hollow, we are quite sure that at the surface, there is much more octahedral to close the structure than tetrahedral units. 25 years after.
Thank you so much. Then I guess we can move to have lunch in the same room as before.
Okay. So good afternoon, everyone. I think we will start with the afternoon session, and I'm happy, let's say, to welcome Professor Samuele Sanna, that is like affiliated as a professor from University of Bologna, and he will talk as a continuity also of the previous talk of Nader. He will basically use the same system as an example, but this time he will talk about the NMR. So the floor is yours.
Thank you very much, Susan, Davide, for this very nice invitation. And this morning, you already saw a lot of spectra, Mössbauer spectra from Mark and another. And now we are going to see a lot of spectra, but this time regarding nuclear magnetic resonance. Okay, so my task is today to talk to you about how we can use nuclear magnetic resonance to study ferromagnetic materials. And here is a list, a partial list of the most important collaborators in this work that we have been doing in the last few years, studying ferromagnetic materials, in particular, apart from my group from the University of Bologna, together with Giuseppe Lodi from the University of Parma. Most of the measurements that I'm going to show you have been performed by Giuseppe. Also with the help of Pietro Bonfà from Modena, and in the last few years we have been also starting collaborating with intensively with the group the CNR in Parma with Franca Albertini, Cesar De Julian Fernandez, and also together with a group of the CNR, but in Bologna with Ilaria Bergenti, Alec Dedio. I will show you some of the results very briefly with the samples from these two groups. And in the last couple of years, also a lot of work have been performed together with a group of Davide here in Genoa. And the work on ferromagnetic materials has been was motivated by the fact that in the last few years there was a lot of effort spent by the scientific community to try to improve the ferromagnetic properties of materials, especially for a lot of applications, in particular for applications in automotive, etc. And for this reason, we have started working in several different projects, also together with other collaborators from the CNR, also together with Gaspar, today is present here, and also some company in different projects, also with the INRIM of Turin. And this is because, as you know, specifically for the electric. So for this reason, we have started by working on several materials that we call the gap rare earth free magnets, because we need to try to cover these intermediate gap applications. But in general, in particular, we considered these intermetallic iron-based materials and the ferrites-based nanocomposites, and I'm going to talk mainly on the second family here. And this is some very general overview regarding what we are doing. Typically, for to have hard magnets, we need to improve their properties. What does it mean? It means that for sure we need to increase the coercive field, because we need a large hysteresis loop. And in general, the magnetic properties of ferromagnets are governed by both microscopic properties such as ordered magnetic moment, exchange coupling, crystal anisotropy, which are material dependent. And extrinsic properties such as the shape, the microstructure, etc., which depends on how we are able to, how to say, you say using to engineering these materials somehow. And specifically, we need to maximize the following parameters. We can split this in two parts. One is intrinsic properties, and the other part is extrinsic properties. Of course, together with these two, we also need to have, or to take care of the fact that we need low-cost materials, abundant materials, environmental friendly materials, geopolitically low-risk materials, and this is why rare earth-free no materials typically, because rare earths are not, unfortunately, they don't fulfill any of these requirements. And regarding intrinsic versus extrinsic properties, we can say that for real applications, we need to improve these extrinsic properties. But the upper limit of these parameters, such as remanent magnetization, cohesive field, are respectively the saturation magnetization, which is related to the ordered magnetic moment, intrinsic parameter, and the anisotropy field, which depends on the ability that we have to move the magnetization in the system. And in order to study these intrinsic parameters, which are the upper limit for the microscopic, for the extrinsic parameters, we are trying to use the nuclear magnetic resonance. Okay, now, very few words about the technique. So nuclear magnetic resonance is a technique which classically, the textbooks, requires an external magnetic field combined with a radio frequency field applied on a nuclear spin ensemble. And typically, the external magnetic field is required to polarize the nuclear spins. And so, if you apply the field along the zeta direction, all these nuclear spins start to do a session around the field applied, and then, since from the quantum point of view, we are interested in the mean value, then the expectation value, then the magnetization is simply the sum of all the magnetic moments, which is along the zeta direction. So for us, our parameter is the nuclear magnetization, which is along the zeta direction. Now, by using a radio frequency, by simply using a coil perpendicular to the applied magnetic field, we can turn this magnetization. From the z-axis, typically we want that the magnetization is on the xy plane where the coil is. In ferromagnets, we can even avoid to use the external magnetic field because the polarization of the nuclear spin is already performed by the hyperfine field spontaneously appearing in the material. Okay? And so you can develop a parallel theory, or analogous theory of this more standard nuclear magnetic resonance by considering the so-called zero field condition, so without any external magnetic field. You can go through this very nice reference about it. This is a less common use of nuclear magnetic resonance. Nuclear magnetic resonance is a very widely used technique. And you can say that there are different NMR, let's say, configurations for different physical, chemical, or scientific problems. No, in particular, we can distinguish between the most common, probably, use of the nuclear magnetic resonance, which is the high-resolution nuclear magnetic resonance, which is very widely used in chemistry, in biology, and etc. And it is typically performed on liquid or solutions. And high resolution, because in this case, for some reason that we have not time now to discuss here, the spectral line are very, very sharp. So you need very high resolution NMR. While on the other side, there is what we call the broad line, or to some extent, the broadband NMR. Broadband, because in this case, when you are measuring solid-state materials, you typically have ferromagnetic and magnetic materials, typically have very large spectral width in the NMR lines. And this is the method which is most commonly used by physicists to study solid-state materials, solid-state properties. Let's say in between, there is this solid state, which is let's say conventionally mainly related to the use of the technique when you have this magic angle spinning effect. We have no time now to discuss this, but just to take into account that there is also this possibility. Sometimes the last two and third that I'm mentioning, they are somehow also used in the same way. Now, going a little bit more in, but not too much, just to say what is the basic principle of the technique. Of course, as we already mentioned, we have the static external field bit zero in general, and the material which is here in a coil with the axis perpendicular to the applied magnetic field. Then you apply a radio frequency field. So this BRF is one important parameter for us, because this is the parameter which allows us to turn the magnetization from the zeta axis to the axis of the coil. And typically we call this the pi half pulse, because we are doing a rotation by an angle theta equal to pi half. And so we do this by applying this radio frequency pulse for the time needed to have the precession of the spins in order that they are laying on the plane. And then we switch off the signal, radio frequency signal, and use the same coil to detect the response of the sample due to the change of the time evolution of the magnetization in the coil. And then you get this time domain signal, which gives you this precession, which is the Larmor precession due to the resonant condition of your system. And then, if you, of course, the signal is maximized when this angle or tilting angle is equal to pi half, because the magnetization is detected by the coil. So, in that case, your magnetization is exactly in the plane where the coil is. And so this is important parameter for what we are going to see later. So you get that the signal is maximized when the radio frequency pulse is calibrated exactly to give pi half. So when this radio frequency field has the proper intensity to get exactly a pi half pulse. Of course, then you can do the Fourier transformation of this time-dependent signal and have the so-called NMR spectrum in the frequency domain, typically. You can also have the absorption and the quadrature component of the absorption. Okay, so now in the case of zero field NMR, where you are using a ferromagnet, then you can even switch off the external magnetic field, but everything is still driven by, of course, the radio frequency field through the coil. And so from the quantum point of view, for instance, if you have a nuclear spin equal to 1/2, you are inducing transitions from the ground state to the excited state in resonant conditions. So you are exchanging the population of these two nuclear levels. And if you are acting in zero field condition, the main contribution in ferromagnets to the external field to the field probed by the nuclei in the system comes from the hyperfine contribution, which is constituted by different, the contact term, the polar spin term, and the orbital term. So you have access to all of these. So you can do this time in the time domain spectrum, NMR spectrum. Then you do the Fourier transformation. You get the frequency of the peak, which is informative about the hyperfine field. So in this way, you have direct access to the hyperfine field. This is an example of the equipment. This is a picture from the Brown University where I was a few weeks ago running some NMR experiment with the spectrometer, the magnet here, and all the equipment necessary to run the experiment. Also here, some picture from the equipment at the University of Bologna for zero field NMR, and also a picture from the very nice lab, NMR lab at the Parma University with Giuseppe Allodi. And what is relevant respect to the comparison with the Mössbauer spectroscopy that we have considered so far is that the NMR active nuclei are so many. This is the periodic table. The yellow nuclei are 1/2 nuclear spin. The blue one are other nuclear spin with greater than 1/2. So you can run in principle NMR on all these colored nuclei. And this helps because it means that we have a high number of active NMR nuclei, either magnetic or not, which means that you can probe both on-site hyperfine fields. For instance, if you do NMR of iron, which is magnetic typically, on-site NMR, on-site hyperfine fields, or transferred hyperfine fields, maybe measuring the NMR on another nucleus, which is not magnetic in that system, but which field the transferred hyperfine field from the nebulous. And so this is a very powerful probe of short and medium range magnetic interaction. What are the main measurable quantities? Typically, the NMR spectrum, and from the Larmor frequency, as we already mentioned, and also from the shape and the width, we can get physical information on the system, and also from what we call the spin lattice and spin-spin relaxation times. This is in addition, for instance, to the Mössbauer technique. Today, we are not going to talk about this, but let's say that in general, from the spectrum, we can get information regarding the hyperfine interactions, while from the relaxation time, we can get information regarding the low energy spin dynamics. But another important parameter that we can measure by using the NMR in ferromagnets is a less known parameter, which is the enhancement factor. The enhancement factor is a parameter which is defined this way, where here we have the hyperfine field, the tilting angle of the electronic magnetization of the electronic spin, and the radio frequency field from the coil that we have already mentioned. Actually, this parameter quantifies the amplification of the radio frequency field at the nucleus due to the hyperfine interaction. But what is important is that this parameter, which can be operatively also defined in this way, is higher when the magnetization, electronic magnetization, can be moved, let's say, more easily. So the easier the magnetization reversal, the higher this enhancement factor. What does it mean? It means that you have a soft material. When you apply a radio frequency field, the radio frequency field, if the material is soft, so the anisotropy field is very low, it means that the magnetization can follow the radio frequency field. If the material is very hard, so very large hysteresis loop, then, of course, the magnetization is the stiffness, if you like, is much bigger, and so you cannot follow the electronic magnetization cannot follow the radio frequency field. And so this amplification effect in the latter case is much lower. So it means that the radio frequency field is only the one produced by the coil, not amplified by the presence of the ferromagnets. So this, in order to give you an example of how this works, I can show you here this experiment, the signal amplitude, NMR signal amplitude on phosphorus in this hard ferromagnet as a function of the intensity of the radio frequency field, or if you like, of the power transmitted by the coil. And you see here that you have two different spectra, one for lower values of this radio frequency field and one for higher values of the high frequency field. The one for high values of the power of high frequency radio frequency field is related to the phosphorus inside the domain wall. And this is because it is harder to move the magnetization when you are exactly in a hard magnet inside the vice domain. And so this amplification effect is lower, and so you need to do a big power to the coil. On the other side, on the other hand, we have this signal coming from the domain's wall. In the domain's wall, the activation energy to reverse the magnetization is lower. So you need a lower radio frequency field, because in this case you have the enhancement factor, because at the end the effective field which gives you the maximum of intensity is the one when you get pi half. The pi half is the same angle for everything, but in this case it is reached for lower in the intensity of the radio frequency field in the coil, because it is amplified by the reversal of the magnetization. Okay, this is an important concept for what we are going to say in a few minutes. Just to tell you that we used very successfully this technique to study these very nice cobalt thin films covered by different cupping layers, to demonstrate that hardening of the magnetic properties of the system is induced by interface molecular interactions. In particular, you can follow in this plot. This is the applied radio frequency power. So let's say the radio frequency field, somehow related to the radio frequency field. You can see that in this material, which is simply cobalt, in this material, which is cobalt covered by fullerene, in this material, which is cobalt covered by gallium-quinoline, you can see that for the two materials covered with the molecular layers, the power requested is higher to get the maximum, which means that there is an hardening of these magnetic cobalt films induced by the coupling, interface coupling with the molecule. Now, I will talk mainly in the last few minutes on the properties related to the study of heterostructures, in particular hexaferrites, by using all these concepts that we have just considered. And in particular, the Miltonian of the system, when you consider a nuclear magnetic resonance, is constituted by different contributions, like the Zeeman contribution, nuclear contribution, electron-nuclear contribution, which is the hyperfine contribution for us, and the electric field gradient contribution. We are going to concentrate mainly only, actually, on this hyperfine contribution, and which gives typically a shift of the spectral line respect to the resonant frequency only due to the Zeeman effect, and this is simply because of the same concept that we have already considered, because we have the hyperfine contribution, which is added to the external magnetic field, if there is an external magnetic field. So this gives you a shift of the frequency or of the applied magnetic field if you keep the frequency constant. Now, one very important difference respect to the Mössbauer spectroscopy that we have considered this morning is the following: that in the Mössbauer spectroscopy we are considering the transitions from the ground state to the excited state, quartet here. While so this gives you the 6 possible lines permitted from these transitions. While in NMR we are considering transitions only between the 2 splitted lines of the ground state, 1/2 ground state. So it means that for each that we have a single NMR line for each inequivalent magnetic state instead of 6 lines for each inequivalent magnetic state. This somehow can, not always, but can simplify a bit the interpretation of the spectrum. So this is the main difference, no, between hyperfine fields obtained by NMR and Mössbauer. Okay, I'm going to skip this part now and going directly to the ferrite-based nanocomposite heterostructure. So understanding why we are interested in that, Nader has already well explained this morning. This is because, just to summarize very briefly, we need to understand how, what is the physics and how to control the magnetic exchange interactions at the interfaces, which is crucial, no, for the development of different next generation nanostructure magnets, spintronic device, where this interfacial coupling can be exploited to tailor magnetic anisotropy, coercitivity, spin-dependent transport property, etc. So the nanostructure that we are considering is the cobalt ferrite combined with a strontium hexaferrite, which we are now using as a model system to probe interfacial magnetic coupling. So this is the system that we are considering, and we are going to see here in CFO the cobalt ferrite and SFO the strontium hexaferrite. Here, what is going to happen here at the interface when we mix the 2 materials? Nanoscopically mix the 2 materials, atomically we mix the 2 materials. And in these materials, Nader already pointed out, we have 5 different inequivalent iron sites, which are reflected in 5 different hyperfine fields, because each iron site has its own hyperfine fields. And this is the spectrum for the reference pure SFO bulk material with these 5 different peaks related to each of these crystallographic and magnetically inequivalent side. We are going in the next to mainly consider these peaks, which are the most intense. We can measure this as a function of temperature, and we see that here is the behavior of the frequency as a function of temperature for each of these peaks. This is in a very good agreement with the same behavior observed also by Mössbauer a few years ago, if we compare the same range of temperature. And so everything is very consistent. And now we are going to compare the spectra of different samples where we are increasing the content of the CFO. Okay, here is a mess, but you can see that there is a change. Don't worry about the detail. There is a change when you add the CFO in the system. This change can be quantified, for instance, by considering the frequency of each peak as a function of the CFO content. And you can see that there is a change. Not only there is a change, but if you compare, for instance, the pure 4 with a 10% CFO sample, here you see an extra peak emerging, which is exactly the extra peak that Nader was mentioning this morning. So I would like to stress that this peak is here, enlightened by the red line, and this is the additional component that Nader has already talked about, observed also by Mössbauer, which is the additional component due to the interface between the SFO and the CFO. So it means that this extra peak associated to the iron 3 plus ions located at the interfacial octahedral sites share between the S4 and CFO lattices, alter the local symmetry and exchange fields due to the interface coupling, and which perturb the hyperfine interaction in the system. But also, as we saw also here, other peaks are sensitive to the presence of CFO, which give us all of these an ambiguous evidence of the interface-mediated magnetic coupling, which means that if the two systems are not talking each other magnetically, then the spectrum should stay constant, the same. But since the spectrum is changing, and in a spatial gradual way, when we increase the CFO content, it means that there is an effective coupling between the two layers. And this is a very successful result for us, because this was exactly what Davide was trying to do, to find a system where we can give evidence of this combination of the exchange coupling due to the interfacial interaction. And I'm going to skip this, going just to the last part, just to say that we have also measured the enhancement factor, of course, for these materials. And you can see what we observed. The enhancement factor, this amplification factor, which is very high for very soft materials and very low for hard materials, changes a lot when you introduce the CFO. Actually, I must say, also with, where is Pierre? Here. With Pierre, we were a bit confused at the beginning, if Pierre, Davide, why this is so high? Because this is a relatively hard material, And so this is because for low CFO content, we have this very anomalous increase that we didn't expect, apparently inconsistent with the large coercivity of these materials. Then we had to consider also that there is a grain size effect in relation to the coherent volume, magnetic volume of the system, which is typically these threshold size. So at the end of the story, this is the interpretation. The NMR response for low CFO content is dominated by spins located in non-uniform spin region, where you have a large incoherent magnetic volume. And so the energy barrier to reverse the magnetization is lower. And this gives you a higher enhancement factor. While when we increase the CFO content, we are closer to the coherent rotation limit, leading to more uniform spin dynamics, and the enhancement factor effectively gets the appropriate value expected for hard materials. I can also show you this by plotting the enhancement factor as a function of the activation volume for the SFO counterpart, derived from magnetization measurements by Pierre, Davide, and co-workers, where the definition, of course, of the activation volume is the standard one, the volume involved in the process of overcoming the energy barriers for the magnetization reversal. And you can see that the enhancement factors drops to the standard value expected when the activation volume is higher than a threshold limit that I'm not going to show you here, that is of the same order of magnitude of the dimensions of the grain size of the materials, which means that we discovered a method how to measure the effective coherent magnetic activation volume in nanoparticles when we want to distinguish respect to incoherent magnetization in the system. Okay, so at the end, it means that increasing the CFO content, we have a magnetically more coherent condition approaching the coherent single domain regime where interfacial superexchange dominates the spin alignment. Okay, I'm done. Sorry. So, in conclusion, I hope that I could give you some example and demonstration how we can use successfully the nuclear magnetic resonance technique to investigate rare earth-free and sustainable magnets, thanks to the properties that we have mentioned, in particular by studying the spectra and the enhancement factor. And in particular, with the last example that I gave you, I think that this is a very good example, which is an effect of a formidable combination. To understand and to study the properties of this material, you first need to have very good materials. As it was already mentioned this morning, you need very good materials. In this case, these heterostructures were wow, because you know exactly what you have. And you have exactly what you wanted. I think at the beginning you already wanted to do that. And then when you have very good material, you can combine both microscopic techniques such as Mössbauer and nuclear magnetic resonance and macroscopic magnetic measurements to understand what is the physics of the system. So in this case, we understood that we have a strong atomic scale interfacial exchange, and through the NMR enhancement factor also we discovered this crossover from incoherent dynamics to increasingly coherent magnetization reversal, governed both by grain size and CFO content. And this helped us to study how interfacial coupling and microstructure govern anisotropy and magnetic reversal in these ferrimagnetic heterostructures. And with this, I thank you very much for your attention.
Thank you very much, Samuele. And then the floor is open for discussion. Pierre?
Thank you for this very interesting. Of course, I already knew some of the results that you are
that you're showing. I just wanted to mention the full story before asking the question, because when we managed to obtain these structures, the very first thing that we did was to send them to Nader for Mössbauer spectroscopy. And in the meanwhile, we were investigating the structural properties, and we found out that we had some relationships, a crystalline relationship between the two phases, but we didn't still know which were the true sites involved. We had some guess, and it was very interesting when Nader contacted us back, because he found that, I mean, it was, let's say, a very nice surprise, because he told us, "Oh, look, this is we see these other sites, we see this other site involved," and the person from the TM, when we did the microscopy, found out that it was the same crystalline site. So it was an independent research. So it was nice to see that without any, let's say, bias, because in science we have also this, right? We are looking for something, but we forget about all the rest. In this case, was a fortunate event. I have a double question, if I may. Okay, one question. The first question is, because you mentioned that you use cobalt, and in your previous study with Mattia and Giuseppe, and now we are studying these strontium ferrite and cobalt ferrite. So they are all hard magnetic materials. Is it possible to do this kind of study also with soft materials, and what could we expect from that in the enhancement factor?
Yeah, it is possible, of course, to do this study also in soft materials. In that case, you expect that the enhancement factor is typically higher. So I think that you can for sure use this also for that. The second question was, sorry. No. Okay.
We can continue the discussion later, because otherwise we are really extremely in delay, and we have people, they will take the train later. Yes, so just maybe here, Davide, just want to make comment about your presentation, then to present the next speaker.
Okay. So just Samuel, first of all, thank you very much. I really enjoy always your presentations, because so it's when you are talking about these really hard topics, to have a capability to transmit the key message is very important. Otherwise, especially for an audience that is not specialistic, is not so. Then thank you very much. Second, very short comment about Pierre. We can tell this small backstage. He was very upset at the beginning of the PhD, because this synthesis method was extremely bad. Self-combustion, I will not get any controlled structure, I will not get nothing. And at the end, you get it. Then I guess that this was very important, because he's struggling a lot, even if the synthesis method was not thermal decomposition and so on. Then thank you very much. Just a few words about the last part of the workshop. I guess that up to now, basically, we introduce General Mössbauer, Jean-Marc give an overview, and Nader and Samuele enter in magnetic materials, presenting, and thank you very much, guys, most of the results that we got together. Now we have two more talks that are, in my opinion, very interesting. There is Roberto Mantovan that will be chaired by Jean-Marc, and Roberto is very important because, first of all, he's Italian representative to IBAME. This is very important, very active, but he will present a very, very interesting application of Mössbauer spectroscopy, showing us that it's possible also to do not only with materials containing iron, but also something else. And finally, Alberto Cini, that is representing a very important group in Florence. I guess that Alberto will basically give us example of synchrotron, mainly synchrotron, then just some different application on Mössbauer. Okay, then the line. Then Jean-Marc, the floor is yours if you want to introduce Roberto.
It's a pleasure for me to ask Roberto to give the next presentation. So I know Roberto for a long time because, of course, we were attending several times the IBAME conference. So just a comment, what is ICAME conference? international conference of application of Mössbauer effect. And the different countries have some representatives. And Roberto is one of the present representatives. I remember now there was Giovanni Principi, there were Massimo Carbuciccio, they were the representative at IBAME. And now Roberto will give some comments on another kind of spectroscopy. I mentioned very briefly this morning that it's possible to do some conversion, and also, as he will present, some emission Mössbauer spectroscopy. So please, Roberto.
Thank you very much, Jean-Marc, and let me first thank you, David and Swosson, for organizing this workshop. I think it's a very interesting event, and it's very important to spread the word of hyperfine interaction within communities that are not always aware about this far less common method, I would say. Now, yeah, my name is Roberto Mantovan, and I'm a CNR CNR guy coming from AIMagn Institute. We have several research units, and I come from the lab located in Agrate Brianza, which is here in the northern part of Italy, and our laboratory is inside ST Microelectronics. Within our institute, our activity ranges from micro nanoelectronics to functional materials and photonics, and we target this from the nanofabrication through the modeling and to the functional demonstration of their properties. And our laboratory was established in 1996. Former name is Laboratorio MDM, and today we are about 40 people. Half of us are permanent researchers, and the rest are students, as usual, and postgraduates. Now, Mössbauer spectroscopy in Agrate is basically summarized in this picture. We have two setups. The first one is conversion electron Mössbauer spectroscopy, which I am very affectionated. Actually, this is a paper, one of the first papers that I wrote in my life, because I developed a version of this kind of parallel plate avalanche counter, which are very efficient in the field of thin films. So we are now moving from nanoparticles and volume materials to typically thin film studies. And in this case, the PPAC detector are very efficient, but there were no variant for performing low temperature measurement with this kind of detector. So this was my work, and in the lab now we can perform SEMS down to 120K. And the reason for that, I can give all the details, is not so easy. You cannot use simple cryostat. And then we recently installed the standard Wiesel bench, which I think is common to most of you, to perform transmission Mössbauer spectroscopy at room temperature. And with some adjustment, technical adjustment, I can also use it for making conversion electron by placing a PPAC detector in front of the source also in this setup. And then, which was mentioned by Davide, in our lab, we are active members of the so-called Emission Mössbauer spectroscopy collaboration at ISOLDE, CERN. Actually, I was introduced to this technique during my PhD thesis, and since more than 20 years, I regularly participated in the team. And therefore, I decided to divide this contribution in two parts. In the first, I will present a couple of examples where we used conversion electron Mössbauer spectroscopy to solve some open issues connected to topics of interest within material science. The first is topological insulators and their interfaces with magnetic materials, non-collinearity effects for skirmions application, and then in the second part, I would move to this far less common strategy for performing Mössbauer spectroscopy at ISOLDE CERN. And here I selected two topics on which I was mostly involved in the recent years now, not so recent, but I would say where I was mostly involved, which are the dilute magnetic oxide and the phase change materials. Now, I don't have to give too much details. Actually, this is just a nice picture showing how it works. Jean-Marc gave a very comprehensive overview in the lecture this morning, but just few words about the detectors that I mentioned. So in this case, I think make clear to all of you how it is very difficult to cool it down. So this is a parallel plate avalanche counter. Actually, it is just think about a capacitor. The sample is one of the electrode, which emits the conversion electrons upon the transition, upon the Mössbauer transition, and you can collect in this anode plate, which is placed in front of your sample, just few millimeters far away, 2-3 millimeters, your conversion electrons. which needs to be amplified, and you do this with a gas that fills your detector, and in general you can use acetone in the gas form. And that's the reason why you cannot cool it down very easily. So to make this at low temperature, it was a very tough job. So this is the detector that we typically use. Okay, and here, since we were discussing also yesterday at dinner about samples, so you can, Gaspar, you can really see here what is the size, okay? So this is 1 by 1 centimeter, and the source is placed in front, as you're here, and of course, smaller is, less effect you have. And if the source is weak, and we all know today how it's difficult to buy a Mössbauer source, it gets very, very long time of measurements. Now, first topic, topological insulators. This is a class of materials that have been proposed now in 2009. I don't want to go off of topic here, but I have to say some basic ingredients. They are characterized by this linearly dispersed band in their structure, and this linearly dispersed band hosts spin polarized electrons. And this is very interesting for application, and actually they are already demonstrated in some application like the spin orbit logic device for reading out the states of a magnetic memory, and spin orbit torque MRAM. So topological insulators are already shown to be efficient. Actually, this is my recent field of research, and we have done a lot of work from the development to the demonstration of effects, spintronics effects in this material. I have to say just few words about ferromagnetic resonance, because it will be importantly connected to our Mössbauer results, which were really critical in order to optimize these kind of measurements. In ferromagnetic resonance, you put a ferromagnet in contact to a topological insulator, because in these devices you need to convert pure spin current into pure charge current and vice versa. This is a very intimate process that makes your device work. And one of the way for measuring this kind of conversion is ferromagnetic resonance. So very briefly, you want to see a symmetric contribution to your signal, which then reverse if you reverse the sign of your applied magnetic field. This is a clear proof of a spin-dependent process into the conversion. Now, what we have done with Mössbauer, of course, you have to interface the ferromagnet with the topological insulator. Being myself a Mössbauer guy, first thing that I've done, I put an iron 57 in contact with it, and in our laboratory, following the production of topological insulator over quite large areas by metal organic CVD, we moved XC2, and that is one of the issues, on an E-beam evaporator, where we put a very expensive iron 57 target, and we deposit 5 nanometer of this iron 57 on top of our topological insulator, which is antimony telluride, and finally capping with the protecting gold layer. Now, this is the set of samples that have been analyzed by Mössbauer, and the main difference is here in red. I don't want to go into the detail of this. I would be happy to give all the details if you are interested. We start from an S-deposited topological insulator, no annealing, no processing, no optimization. And then there is another sample called the pre-annealed, where the substrate is annealed before the deposition, and finally with the post-annealing. When all this is done simultaneously in the same growth, we grow the iron 57 and the capping gold on top of these 4 samples. So they are all nominally identical for what concerns the iron. This I can really skip. We are looking to hyperfine interaction. We are very well introduced by Jean-Marc this morning. So with SEMS, you are just probing the same thing. So the valence states, the local symmetry, and the hyperfine field if present at your iron site. We start with a reference sample. We were quite happy this process. After very few trials, we have been able to produce quite a pure iron layer with some mixing coming with it, from the interaction of the iron with the top gold, and possibly some silicon, some silicides formation, which is quite well known in this. But that was the astonishing result, which gave us the first very important information from the Mössbauer, that when you grow your iron layer on top of an S-deposited topological insulator, there is a huge contribution from the center coming up. And this is bad, because if you want to develop processes for spin-charge interconversion at this interface, of course, you don't want to have paramagnetic phases at the interfaces. When we move we identified this also. We had few papers about that, 2-3 papers discussing this. We identified this doublet, central doublet, with the formation of a sort of intermetallic iron tellurium, also combining with many other techniques like TOF-SIMS, XRR, because this is always necessary, as Jean-Marc very nicely stressed this morning, in order to have a final picture. So details are all in these papers, and we are sure that at the interface here, there is this formation of iron tellurium. But when we move to the sample where the topological insulators start to be optimized, we see that this contribution collapses. And following the post-annealing, it goes even better. So we basically restored at the interface between iron and antimony telluride a sort of reference situation for what concerned the properties of iron. So we were happy, and we were ready to probe spin charge conversion in this kind of heterostructure. And we start from FMR. Will not give details, but just show here, point attention here, that the slope for the samples on top of the topological insulator jumps up when compared to the reference. This is connected to the damping effect that you have in FMR, and very often in the literature, this is attributed to a spin pumping process, so an efficient spin charge conversion. But if you do it electrically, which we have done, we do not see any electrically detected spin charge conversion, even if by Mössbauer we were able to get a pure interface. Because in this case, you would expect when you reverse the magnetic field here that the symmetric part jumps reverse exactly, while this doesn't happen. So Mössbauer spectroscopy was very helpful to say this is not enough, so you must do something else. So the idea was to protect somehow from the magnetic perturbation of the iron the topological surface states of our material, and we have done this by changing a bit the strategy and introducing a gold interlayer between iron and the topological insulator, and go again to our spin charge conversion. And of course, we checked by conversion electron Mössbauer spectroscopy both the sample, the reference, and the one with the topological insulator. We see mostly pure alpha iron, and in this case, we have been successfully looking and measuring to a very clear spin charge conversion. So this is an example how Mössbauer spectroscopy, in this case conversion electron Mössbauer spectroscopy, can be really helpful in understanding something of some peculiar properties, interface-based properties in very new and interesting materials such as topological insulators. Now, the second topic where we more recently used SEMS is interface magnetism for skyrmions. Now, very briefly, skyrmions are these topologically protected magnetic figures that can be stabilized in ultra-thin magnetic layers. And in principle, it originates for when there is a non-vanishing so-called interfacial Jałodziński-Moria interaction. And it is expected to take place when you have very thin, down to 1 and below 1 nanometer ferromagnetic layers. And one technique to measure it is Brillouin scattering. And so we did this with this recent paper. You can find all the details. Gianluca Gubbiotti was doing the Brillouin scattering in these two samples. You see the iron here was quite thick, 2 nanometers. We didn't expect to see Jałodziński-Moria interaction. Actually, we didn't want to look for skyrmions, so it was totally another reason why we did that. But very interestingly, we find that there is a shift in the BLS spectrum when your iron is on top of platinum, but still quite thick, around 2 nanometers. And in order to understand the origin for this Jałodziński-Moria interaction, we went to our Mössbauer setup. And here, I say thank again to Jean-Marc for having explained what are the meaning of the relative ratio between Mössbauer lines. So here we get 3-4-1 in the case of iron on top of silicon oxide, meaning that you have a fully in-plane magnetization for your iron. But something very interesting happened when we moved to the sample on top of platinum, where to interpret satisfactorily the data here, I needed to introduce an additional layer, an additional iron contribution, so-called iron 2 here, where the ratio changed. So it started to be less, so 2 somehow 3 and 1, meaning that there is some non-collinearity that appears when you grow your iron on top of platinum. And this came to us to propose this model. Of course, we didn't do depth selective, so we cannot prove it directly, but we proposed that this additional contribution of slightly out-of-plane magnetization most likely come at the interface with platinum, which is quite known, not in these thick materials, but for ultra-thin iron, it is known. And we tentatively attribute to this the formation of the Jean-Marc interaction. So it was very nicely showing the Mössbauer spectroscopy that there could be some space for having perpendicular magnetic anisotropy and potentially skirmion formation, even in relatively thick ferromagnetic materials. And now let's move to what was introduced already by Davide. The second part of the talk, I'll present some far less common strategy for making Mössbauer spectroscopy, in principle, in iron-less materials. Why? Because you put yourself iron into the materials under analysis. We do this at CERN by making use of the proton coming out from the proton synchrotron, okay, which is here. At CERN, the proton synchrotron are injected in the superproton synchrotron that finally injects into the LHC, where they do the fantastic basic physics that we all know from journals and newspapers. But at the proton synchrotron, you can still make something very interesting in solid-state physics. So this can be used to induce nuclear fission in targets. In our case, we used uranium carbide targets, and plenty of species of atoms comes out following the nuclear fission, and then following a very precise and accurate laser ionization, you can produce a highly pure beam of manganese 57, highly pure meaning 99.9 and something percentage, and this can be directed to your implantation chamber in your sample, which is as usually 1 by 1 centimeter typically, and it decays to the Mössbauer level of iron. So from manganese 57, it transforms to the iron 57, and this makes your sample the source, okay? The main highlights of these methods is that it is 100% selective to what you put in. So you just see what you are implanting in your sample, and you can make useful spectroscopy in an extremely dilute regime. Up to 10 to the 10, 12 atoms is what you need, which correspond to 10 to the minus 3, 4 atomic percent in your implanted sample to have a good quality spectrum. And then you probe the usual things, so the hyperfine interaction that you are interested in. And if you are interested on the real basic and on the start, all started with actually by the group of Professor Weyer, and this is a hyperfine interaction paper from 2000, which is very instructful to start with. And this is a picture showing, I mean, it's some sort of synchrotron. So this is where the Mössbauer setup is every time set it up. So contrary to a synchrotron, there is no one there doing things for you. So you go there 1-2 weeks before, you set up everything, and when you are happy, you ask for protons and you do your experiments, and can be tricky. Now, I'm here to say the good things, the bad things at the coffee. And this is a closer look of the setup. The setup at the end is a conversion electron Mössbauer setup. You have a drive, and here is the detector, and it's the detector that is moved in order to perform the spectroscopy. The sample is here in blue into your implantation chamber, and this is the beam of manganese 57 coming through. And then upon implantation, you record your data with the parallel plate avalanche counter placed in front. Now, this is what I just said, but just to make it clear, you can reach the Mössbauer level in 2 ways at Isolde, actually. The main one that we used is this. As I anticipated, you implant manganese 57. This is an half-life of 1.5 minutes, meaning that you have few minutes to perform your spectroscopy, okay? Which is good from one side, because then you can take your sample. It's after 15 minutes, it's basically non-radioactive, and you can do other things. but you have to really run. Be there. You cannot leave your machine as in the lab and waiting for eye statistic. You must be there and change sample when you are happy. And there is also another way, which is less common, but we used in the past, which is to implant the cobalt-57, basically to build up a source into your sample. But of course, it's 10 to the 10 to the 12. So you cannot, I'm telling you, we cannot make a source that then can be used in the lab. But you can produce the long-lived sample that you can bring at home if you are allowed of handling radioactive samples. And in Leuven, they were very expert in doing that. And you can then use your sample as a source, even at home. Now, the first topic that I want to propose, I'm very, enthusiastic of this. We were all very enthusiastic because it was really, really funny, I would say. The topic of dilute magnetism in oxides and semiconductor is a topic that emerged in 2000, where the group of Thomas Dietl proposed a very high Curie temperature in basically dilute system where they put almost a negligible amount of manganese, and you can see that from 2000 up to 2015, for 10 years, the number that yearly were published in the topics were really, really high. And there was indeed in the first half of the 2000 so-called, I like to call it as an optimism area, where we were all very convinced that that was possible, but then a super instructive title by Mike Coy starts to underline some doubts. So is this fact or fictions? And the main problem were that people doing, even Mössbauer in the lab, in order to have the signal, they needed a fraction and a concentration of magnetic atoms that typically gave precipitates. So at the end, you were looking to magnetism originated from precipitates and not real dilute magnetism as we were hoping, or unwanted contamination. And there are long stories by handling with improper tweezers your sample and see signal in the squid, for instance. So there was a lack of methods that can get rid of this. And we were trying of doing something here. That was astonishing. It was the optimist part of the story also for us. In 2005, we did the first experiments on single crystal of zinc oxide, and this is a super clear magnetic fraction that we observed upon implantation of. We are here at 10 to the minus 3 for atomic percent of manganese, and then that decays to iron, and the magnetic fraction up to 70% was seen up to 600 Kelvin. And being the older group was quite polarized around this, and so quite optimistically we attributed this to defect-induced magnetism, which is one of the most credible theory at the moment. And this is a typical lead that we use at Isolde. You can see 4 holes. You can place 4 samples at once, and then by moving these halogen lamps up and down, you can anneal them locally from room temperature up to 500. So you can make a lot of measurement by changing the sample and then implant again. Due to the tiny fraction that you introduce every time, you don't risk to have precipitates because you are in a real extremely dilute configuration. But now, if you have a ferromagnetic material, you have a sextet. But if you have a sextet, do you necessarily have long-range magnetic ordering? That was, of course, our question and the question for everyone at the time. And being then probably started to be more polarized by criticism, we built at that time a special lead which allowed to make our experiment under an applied permanent magnetic field, 0.6 Tesla, and rotating the sample, okay? Which, as was explained this morning already, in the case of a long-range magnetic interaction, so volume magnetism, real dilute magnetism, you would see, as far as you go parallel with your external applied magnetic field to the gamma, okay, you will see a collapse of the inner lines from 341 to 301. And of course, we cannot do exactly 090, but there is X here in between. Okay, the theory is quite well accepted there. And this is what we measured. So look at the middle lines. They were not collapsing where we move the parallel, which is in this configuration. But what happens was very clearly pointing to other things. And in this fit, actually, the 3 separate Kramer's doublets were used that were nicely following the angular dependence that were expected. So this comes from slowly relaxing paramagnetic centers. Went down to theory, and there is this nice chapter of Morup in the Philip Gutlich book that was very instructive. If you have paramagnetic iron in an axially symmetric crystal field, and this happened only for the 3+, because of the symmetry, okay? They're spherical. If you have these conditions, you could have that from a more complicated Hamiltonian, you have these 3 separate Kramer's doublet, which separately follow the angular dependence. And by using this analysis, we find that at the end, we were dealing with slowly relaxing paramagnetic center. No trace of long-range ordering in the extreme dilute case. Unusually long relaxation rate, of course. With Mössbauer, you cannot measure directly spin lattice, spin-spin, but we did something that I will show in the next slide by judging the temperature dependence of the average line width. You can somehow extract the spin relaxation, okay? And then by doing a temperature dependence, you can identify whether there are more spin lattice or spin-spin relaxation. But before saying that, at that time, we measured the relatively long spin relaxation 10 to the -5, contrary to other oxides where we measured much shorter relaxation time. And probably there could be still some interest. I'm not following really this kind of physics, but at that time appeared a paper that proposed iron 3+ as a possible spin qubit option in zinc oxide due to long spin coherence length that here was measured by EPR. But the story was not concluded. So after 10 years, first experiment 2005, now we are at 2015. This is the story so far. We know that at the ultra-dilute regime, we are dealing with slow relaxing paramagnetic center. The literature concentrations, which were typically used by people doing Mössbauer spectroscopy, the group of Kai Potzker did a lot on that in this direction. They observed that finally they have precipitates when they see ferromagnetism. But what happened in between for all of us was a sort of mystery. So could still be any possibility of having long-range ferromagnetism at some point, which is, I don't know, we didn't know whether it could happen at some precise concentration. And to do that, we prepared a set of samples by making pre-implantations in the lab and then implanting at CERN. So we scanned basically all the range from the ultra-dilute regime up to few %, which is what I like to call the literature concentration typically used. And these are the results, okay? What I anticipated here, this is the relaxation rate that we extract from the broadening of the lines. And in the ultra-dilute regime, we are somewhere there. And gradually you move to a temperature-independent process, which to us was the signature of the first spin-spin relaxation, meaning that your iron 3+ start to form the very early formation of clusters. And look at that. That was happening at 0.2 atomic %. So we were tracking somehow live the gradual transition from the ultra-dilute slow relaxation center to spin-spin relaxation due probably to the formation of clusters. So this for us basically closed the story, and we concluded that at least in this condition, you can never say forever, but in these conditions to have a real genuine dilute magnet is not possible. Either you get clusters or it's slowly relaxing. You cannot claim anything about long-range magnetic ordering, unfortunately. 10 years to discover that the answer was the bad one, but that was the story. Now, I will conclude with the final example where we use the Emission Mössbauer spectroscopy in some topics that are mostly connected in solid-state physics, material science, which are phase change materials. Phase change materials, probably you are aware of that, they show a rapid and reversible resistive switch from high resistance in the amorphous states to low resistance in the crystalline phase, and they are used for memories. When we were used to DVDs, optical disc, PCM, phase change materials were at the basis of this process, but nowadays they are used. Actually, ST use it for devices at the solid states. So it's very interesting material. They are sold already in several devices, but the mechanism that are at the basis of this phase transition at the atomic level are still under debate today, and at that time they were for sure. So what we did, we fortunately had access to a state-of-the-art sample, germanium telluride from what was at that time Mnemonics, then changing Micron, big companies. And in one of them, in our laboratory, we tracked the phase transition by doing resistivity versus temperature, and it showed what was expected, and we identified at 180 Celsius the transition temperature. And then with the second one, we went at Isolde. In my opinion, that was a beautiful experiment, one of the more exciting experiment that I've done, I have to say. Probably because it was done 2 or 3 in the morning. So it was also, getting all tired. No, wait, we have to wait for the transition. So we did exactly the same that we do typically by using our standard lead for an in situ annealing. And this is the first spectrum that we got in the amorphous states. So it was our 0. Room temperature was very hot. It was August. So our room temperature at that time in the hall was 36 degrees. And there is two signals, okay? One quite broad but single line, identify as A, and then this doublet, broad doublet. And then we get close to the transition, but still before the transition, and nothing happens. But here, boom, across the transition, we see clearly the emergence of a new component. And all this was done 10 minutes, 10 minutes, and 10 minutes. So all the experiment is less than an hour. And so it was clearly connected to the macroscopic transition that we know it exists. And now we have 2 components. And then if you go on, you cannot reverse because this is done only with very fast laser processing, so not with the halogen lamp. You just provide additional thermal budget and the C component goes up. So we identify 3 components in the 2 configuration, the amorphous one and the crystalline one. And then we need to understand from where it comes. DFT was absolutely necessary in this case. And at the end, we identified the single line of the amorphous states as being the iron substituting germanium and looking what happens around at the tetrahedral site. In the crystalline phase, the C component was still iron sitting there. In the octahedral configuration of 8 surrounding tellurium atoms, and the broad doublet, which mostly due to damage, implantation-induced damage, which is a cons of the method. You are implanting very few atoms, but you are implanting, so you have some sort of damaging. It was this additional doublet. So to close the story, we have been able to make, by emission Mössbauer spectroscopy, a sort of atomic scale pictures of the amorphous phase and the crystalline phase by following it in situ. All this by putting a total of 10 to the minus 3-4 atomic percent of iron, which in these cases served as a local probe in a material that was totally ironless, okay? So, of course, matching with the theory in this case was absolutely necessary. Now, I don't have a conclusion slide because I hope I gave some separate conclusions step by step in this example, but just conclude with this one. As Davide said, the particular of this method is that you can perform this spectroscopy ideally on all the materials, regardless they have or not iron. And this is a list that I took on papers that we published in these years, probing hyperfine interaction in them upon implantation. In some of them, there is manganese, and this is nice because you expect that your manganese goes there. So you expect it's substitutional and you look what happens around. But then there is the bad. If you start to be interested in using this method, we are currently experiencing what they call long shutdown, number 3 at CERN, because they regularly do maintenance, big maintenance, mostly due to the LHC, but all the facilities are affected. But next year, probably in the second half of the next year, they will start to accept again proposals on solid states to perform spectroscopy in 2028. This is because before that, this kind of experiment there are impossible. But in the meantime, thanks mostly to the work of Juliana Schell, that is the solid-state physics coordinator at CERN, and in contact with the Ilmenau group, they did a very big upgrade of the system. So our hope is to have a real upgrade of our implantation facility for that time. And so to start with, if you feel you can be interested in this, start to feel in contact with me. I can forward eventually the request to CERN, and we can discuss whenever you want possible experiments. There will be huge possibilities in terms of temperature range, applied magnetic field up to 2.5 Tesla, angular dependence. So a lot of new physics possibly can be discovered there. And I mean, as synchrotron, you all know, it's always very funny. Not always. And thank you very much. I thank you with this. I think this picture was taken there a few days before the shutdown, so I never came back there.
Okay, so thank you, Roberto, for this nice overview, nice panorama on the conversion on emission Mössbauer spectroscopy. So with this presentation, for people who are not very using with Mössbauer, now they have a total view on the Mössbauer. Okay, so any questions or comments? Yes? Yeah.
It's possible to do this type of measurements in operando. So let's say by injecting current, let's say spin polarized current, to see if it's possible to test the environment. No.
Many meetings discussing this upgrade, and that was my first requirement, and there were some PhD students working on this till now. To be honest, we can't promise it. It would be very nice. It would be very nice, but we are not ready for that.
Also?
It's following the lines of the previous questions. Maybe you cannot apply a current, but can you apply a stress, like in piezoelectric materials?
We never did it. Probably to put a piezo somehow could be not so difficult in my opinion, but we have never done. I put it in simple words, but it's not so simple to do everything. Then everything is radioactive when you implant. You have to wait a bit, okay, but I mean, some things to be considered.
We have also some questions from online, Alexis. So just give me. Alexis.
Yes,
Alexis, can you hear us?
Thank you very much. Greetings to all the people there, and greetings, Jean-Marc. How are you?
Fine, on you.
Fine, thanks. And all the other people there, Sosen, Davide. Very nice. Thank you for the very nice talk, Dr. Madovan. A question on iron doped zinc oxide. Does the valence of iron play some role in the properties of the material? Because I think that chemically, iron 2+ meets more the zinc oxide ion as a material. But iron enters as a 3+ state, and this might causes, let's say, more complexity, because it goes towards the ferrite properties.
Thank you. Sorry.
In the zinc oxide. Thanks.
Yes, thank you very much. Very appropriate question, and thanks for saying that. Of course, in these 10 years of work around zinc oxide, after we discovered that that was a slowly relaxing paramagnetic center, it was 3+. So if you have 3+, you can have this slow relaxation. If you have 2+, you don't have, because you change the symmetry from spheric to more complicated, so it doesn't have this property. And that's why we were looking and implanting, I don't know how many crystals, to any trace of iron 2+, giving signature of magnetic ordering. That was our last trial there, and we never saw it. Because if you see a 2+, that it broadens and change by applying the magnetic field, then you can, as you very nicely say, claim that there could really be a possibility for long-range interaction, but unfortunately, we didn't see it. Thank you. Very, very, very nice question.
Thank you. Thank you. Thank you for the very nice talk.
Thank you, Alexei. So I have a comment. Other comments? So I have one comment. If you want to to improve your system with SEMS, maybe you can contact Jean Jurasek in Rouen, who was able to perform some SEMS measurements at 77K and even at lower temperature. In addition, he was able to apply a canal magnetic field. It was the idea. I expect that now he was successful. Yeah, because it's very interesting to do some in situ measurements. So I will shift to another topic. So it is about corrosion. So at one period, there was some studies on corrosion, and people was obtaining some same spectrum. So very, very strange. But it was difficult to fit. And they have only one spectrum at room temperature. That I was telling this morning that it's rather frustrating to have a single one. So by decreasing the temperature, it's a good way to improve, because you have probably a lot of nanograins at room temperature. On the second comment, I forgot what it was. It's how to fit your SEM spectra.
How do I fit? I use a Vinda software package done by physics. Well, Lorentzians. These are Lorentzians, of course. Okay. And
you did not consider that you have some retro-diffused electrons which are coming from low, from big depth, and the other ones who are coming from surface?
Of course, this is
integral.
Of course.
Okay.
No, if you are referring to the experiments where the different iron 57 on top of the topological insulator, it is all 57 iron. So to get information from the interface, that's the reason why I always use references. So it was done by comparing different samples, but from the technique itself, from a single sample, you do not know from where it comes. Absolutely, that's integral.
Okay. And the last comment is about your experiments in the first part, when you have introduced some gold and also some nano layer of iron, because 2 nanometers. That means, is it 2 nanometers? Because there is probably some roughness and there is also some diffusion. Did you check it?
Yes, of course. We always do the both in general TOFSIMS, time of flight secondary ion mass spectrometry in several points, and XRR. XRR is the method to see that you are continuous. That's the reason actually we use at least 2 nanometers. If you go below, you have islands, you don't have a film at all. Absolutely, yeah.
So I want also to make a comment that sometimes what is very interesting is to play with iron 57 on iron 56, because iron 56 is mewed for Mössbauer spectrometer. Sorry? Even better, but it's much more expensive.
The Russians, many times. Many years.
Okay, not now. Okay, so thank you very much, Umberto, again.
So, excellent. So now is your turn, finally, for the last speaker of this day. And I'm very happy to introduce you one of the most brilliant young researchers that we have in our community, Alberto Cini, who is going from the University of Florence, who is going to talk about how we can use synchrotron nuclear inelastic scattering to study vibrational modes in this iron spin triangle. Please.
Okay, thanks for the kind introduction. Yes, today I will show some recent works concerning Mössbauer spectroscopy and with synchrotron light. But before entering the topics of this talk, I would like to recall some basic ideas on Mössbauer spectroscopy. So, Mössbauer spectroscopy is a technique based on the resonant absorption and emission of gamma rays by nuclei in a solid. So it relies on the Mössbauer effect that was observed in more than 100 nuclear isotopes, the most studied of which is probably iron-57, for which we need gamma rays with 14.4 kiloelectron volt. To have the Mössbauer effect, we need the process to be recoilless, so the nucleus must emit this gamma ray without recoil. The probability for Mössbauer effect is the so-called recoilless fraction, or Lamb-Mössbauer factor, which depends on the wave vector of the gamma ray and on the vibrational properties of the lattice. So, Mössbauer spectroscopy is a very sensitive technique with an energy resolution down to 10 to minus 9 electron volt that allows to study the hyperfine interaction of each iron nucleus in the sample. So, from the isomer shift, the quadruple splitting, and the hyperfine magnetic splittings, we gain information about the chemical, the structural, and the magnetic properties of the material that we are studying. In a standard setup, like the one that we have in Florence, the radioactive source is mounted on a transducer that goes back and forth in order to modulate the energy of the gamma rays by means of the Mössbauer effect, by means of the Doppler effect. Then the gamma rays interact with the sample, and the transmitted gamma rays are revealed. The sensitivity of a standard setup is suited to study bulk samples. So, in other words, principally to study powder samples. If you want to study thin or ultra-thin samples, then you have to consider synchrotron light, as was the case of a monolayer of single molecule magnets sublimated on a gold substrate. So, first of all, what is a single molecule magnet? Single molecule magnets are molecules that exhibit a slow relaxation of the magnetization at low temperature of purely molecular origin. They are constituted of a magnetic core surrounded by ancillary ligands that shield the system from the outside. So, in the end, these molecules show a large value of the total spin S and an easy axis magnetic anisotropy. So, if we give a look at the energy as a function of the magnetization direction, we see a double well energy potential, and inside it we have 2s plus 1 discrete quantum energy levels, with the lowest lying corresponding to the maximum spin projection, plus s and minus s. So, this system shows this magnetic B-stability, and because of these features, because of this peculiarity, they have been proposed for innovative applications, such as high-density information storage, quantum computing, or molecular spintronics. But in order to really use these molecules in this application, we need them to maintain their magnetic properties when they are deposited on a surface, as they would be in one of these devices. What we wanted to study was a single molecule magnet called iron-4. The names come from the fact that it is composed of 4 iron ions. 3 are at the vertices of an approximately equilateral triangle, and 1 it is in the center. They are antiferromagnetically coupled, such that the result is a total spin ground state with S equal 5. The molecules were enriched in iron-57, and then they were deposited on a gold substrate. 2 samples were synthesized, a dropcast one, so a very thick one, 100 nanometers of molecule, and a self-assembled monolayer, which means just one layer of molecules less than 1 nanometer on gold. As I said, the problem is that the standard setup does not have enough sensitivity to study these kind of samples. This is why we consider the synchrotron light, and in particular the synchrotron Mössbauer source present at the ID14 beamline at the ESRF synchrotron in Grenoble. This is a sketch of the beamline. So how it works. The broad synchrotron light is then filtered such as that only gamma rays with 14.4 kiloelectron volt are selected. Then the bandwidth is decreased in 3 steps. First, by means of common monochromators. Then, by means of a nuclear monochromator, which is an iron borate crystal, a high-quality crystal that is kept in particular conditions of temperature and external magnetic field. In this way, it behaves like a nuclear monochromator, such as the radiation inside it does only pure nuclear refractions. So, out of this iron borate crystal, the bandwidth is around 10 nanoelectron volt, and the intensity is of the order of 10,000 photons per second. So now it is instructive to compare the specification of the synchrotron Mössbauer source with those of a 10 millicurie source in the classical setup. Concerning the photons per second, the value is practically the same. And concerning the line width of the synchrotron light is 3 times that of a standard source, but with synchrotron line, we can have a focal spot of the order of micrometers. Moreover, we can do the experiments in transmission, but also in grazing incidence geometry. Grazing incidence means that the radiation arrives on the substrate and is reflected by it at an angle of the order of 0.1 degrees. Thanks to this peculiarity, we got a better sensitivity that is of the order of 2 orders better sensitivity than the standard setup. So here you can see the Mössbauer spectra from the thick samples that were made to as a test of the technique. You can see that at the lowest temperature, 2 Kelvin, the spectrum is essentially a sextet. Then it collapses to a single central line around 40 Kelvin. And here we have the Mössbauer spectra of the monolayer sample. These were the first spectra from a monolayer of molecules. The trend is similar to what we see in the dropcast. Clearly, the signal-to-noise ratio is worse as we have less intensity. What information comes from these spectra? We have to look at the fitting. So here, for example, we have the spectrum of the thick sample at 2 Kelvin. It is a sextet, but we see that we have also a kind of structure, meaning that we have inequivalent subspectra inside it. So in the fitting, we considered the presence of 4 subspectra, considering that we have 4 iron ions inside it. And the result was that 3 of them have very similar values of the hyperfine parameters. So they are the 3 ions situated at the vertices of the triangle. So the geometry is really very similar to an equilateral triangle. While the ion at the center feels a different environment, so it feels values of the hyperfine parameters that are a little bit different from the others. Concerning the monolayer sample, we used the same fitting procedure, except that in order to consider that the lines were broader, we had to consider a Gaussian distribution of the electric parameters. And this translated into the fact that we have differences of the order of 0.04 angstrom in the iron ligand distances from their average positions. These local deformations were undetected by other techniques, other X-ray characterization techniques, but were confirmed by AIMD calculations. So, in conclusion, we demonstrated that with the synchrotron Mössbauer source, we could have information on the hyperfine parameters of very thin samples. But what about if you want to study the molecular dynamics? Then also in this case, you may want to use synchrotron light with a technique that is, I would say, complementary to Mössbauer spectroscopy, which is nuclear inelastic scattering. Nuclear inelastic scattering is a synchrotron-based technique that relies on the simultaneous excitation of a nuclear resonance and molecular vibrations. So, at difference with Mössbauer spectroscopy, where we have elastic absorption, so no recoil of the nucleus, in nuclear inelastic scattering, you have inelastic absorption, meaning that the nucleus has a recoil, or in other words, phonons are involved. Moreover, the energy is dissipated through the emission of electrons from outer shells, and consequently, we have the emissions of fluorescence. So, gamma rays would have an energy lower than the energy of the incident gamma. The probability to have nuclear inelastic scattering is then 1 minus the probability to have the Mössbauer effect. As for the Mössbauer effect, we can modulate the energy of the gamma rays in order to detect the frequency distributions of the lattice vibrations. In fact, if we look at a typical nuclear inelastic scattering spectrum, we have the counts as a function of the energy of the gamma rays. And what we see usually is a central line corresponding to elastic absorption, meaning gamma rays with an energy that is equal to the energy of the resonance. But we have also sidebands for gamma that have energy greater or less than the energy of the transition, meaning that we have the possibility to create or to annihilate one or more phonons. And by proper data analysis of these nuclear inelastic scattering data, then the density of the phonon states is calculated. Technically, nuclear inelastic scattering needs synchrotron light because we need a high brilliant source and also the possibility to sweep a wide range of gamma ray energies. This is why we considered again the ID14 beamline in Grenoble. Like for the SMS, the 14.4 kiloelectron-volt gamma rays are selected. Then only the monochromators are used to have a bandwidth of the order of millielectron-volt, so broader than the one of the SMS. Then the gamma rays interact with the sample, and what is detected is the fluorescence. So gamma rays that now have an energy of the order of 6.4 kiloelectron-volt that are emitted with a delay of the order of nanoseconds with respect to the interaction. At the same time, also the nuclear forward scattering, which means the elastic absorption, is detected, but is for technical reason and for data analysis. So in the end, nuclear inelastic scattering is a fast technique, also precise because we can focus the beam. Moreover, the resolution is under 1 millielectron-volt, so a resolution that is comparable or better than the resolution of neutron scattering or X-ray scattering. But we have a limitation. Okay, the pointer is not going anymore. Okay. The limitation is that what we are sensing is a partial density of states with partial meaning only the density of states relative to the iron ions. What we wanted to study in this case was an iron spin triangle. In this case, the core of the molecules is constituted by 3 iron ions, antiferromagnetically coupled, at the vertices of an equilateral triangle. The molecule crystallizes into crystals that are elongated one axis, that is the C-axis, that is perpendicular to the plane of the triangles. Why we're so interested in this spin triangle? Because we are interested in antiferromagnetically coupled spin triangles in general, as they are systems where the spin electric effect is predicted. The observation of spin electric effects is one of the focus of my research activity, as you can see from recent papers. With the spin electric effect, we mean the possibility to manipulate the spin of a system by means of an electric field, rather than by means of a magnetic field, so rather than by means of Zeeman interaction. Why? Because this electric manipulation would have great advantages with respect to the common manipulation in the field of quantum technology. But first of all, we did a preliminary study of this spin triangle. In particular, first we studied the powder as a function of the temperature. These are spectra taken with our spectrometer in Florence. So we went from room temperature to 80 Kelvin with nitrogen, and then from 80 to 3 Kelvin with helium. The spectrum is a doublet and practically does not change with the temperature. For the fitting, we considered only one doublet, and the result was that the line width is rather broad, something like 3 times the natural line width. This possibly indicating the fact that, yes, the molecule has an equilateral geometry, but it is an approximate equilateral geometry, so we are sensing 3 slightly different iron environments. Then, as a further test, we measured a Mössbauer spectrum at room temperature of a crystal of this spin triangle. To do this, obviously for sensitivity, because of the better sensitivity needed, we considered the synchrotron Mössbauer source, and this is the spectrum taken with the gamma ray wave vector perpendicular to the c-axis and the polarization of the synchrotron light parallel to the c-axis. The values of the hyperfine parameters are in line with those found with the powder, as expected. The spectrum has an enhanced asymmetry with respect to the spectrum of the powder, probably because in this case we are sensing only one orientation and not all the orientations like in the powder. And then we can see the nuclear inelastic scattering data. First of all, data from the powder. At the left, you can see some nuclear inelastic scattering data at a different temperature, showing the elastic peak plus sidebands. At the center, you can see the partial phonon density of states that we have calculated at 11 Kelvin. So you can see that we have a broad feature under 10 milli electron volt, and then we have sharp peaks, multiple sharp peaks at higher energies. We repeated this measurement at various temperatures between room temperature and 6 Kelvin. The spectrum remains practically the same, indicating so that the vibrational dynamics is practically the same in this thermal range. And then, from the density of states, we could also calculate a number of thermodynamic parameters, like the total vibrational amplitude, or the specific heat, or the vibrational entropy, or also the F factor, the Lamb Mössbauer factor, which theoretically is determined in a more reliably with this calculation that with the common calculation based on Mössbauer spectroscopy, as here the recoil fraction or the sample thickness is not present in the calculations. And then we have the really core measurements, the core nuclear inelastic scattering measurements that were realized on the single crystal of this spin triangle. What we can see now, it is the projected partial iron density of state. Projected in the sense that each phonon is weighted by its projection on the direction of the gamma ray wave vector. In fact, we did the experiment in different orientation. So the red line is the experiment with the gamma ray wave vector parallel to the z-axis, while the blue line is with the gamma ray wave vector perpendicular to the z-axis. And we can see that we have different peaks between the two experiments, meaning that we have different vibrational modes depending on the orientations. Moreover, if we consider the green line, then that is the experiment done at an intermediate orientation. This has peaks from both the two extreme orientations. It is similar to the powder as expected. And finally, we remounted the crystal in order to have the gamma ray wave vector always perpendicular to the z-axis, but with the possibility to rotate the crystal around its z-axis. So in this case, we could do the experiment with different orientation of the gamma ray in the plane of the triangles. Here, blue and red are two orientations differing by 30 degrees. We can see that the spectra practically overlap, meaning that we have an isotropy of the vibrational modes in the plane of the triangles. Okay. And we were very satisfied by this data that were useful for the validation of the vibrational calculations. These calculations are ongoing, so I show only some preliminary first principle calculations that confirm what we have seen in the experiment. For example, the fact that if we consider the gamma ray parallel to the z-axis or perpendicular to the z-axis, we have different peaks. And also, if we stay with the gamma ray perpendicular to the z-axis, and we experiment different orientation in the plane of the triangles, then the spectrum doesn't change. So these calculations will be refined, also because the focus will be to understand what are the preferential vibrational modes in these molecules. Why is this important for the Mössbauer, for the spin electric effect? Because if along a direction we have a preferential vibrational mode, then it is more probable that if we put an electric field along that direction, then we can see a spin electric effect along that direction. So, in conclusion, to sum up, at the end of this day, you have seen that if you want to know the hyperfine interactions or the spin dynamics in a system, you can use Mössbauer spectroscopy. If your system is very thin, then you have to consider synchrotron Mössbauer source. And if you want to have information about the phonons, so about the vibrational dynamics, then you may consider nuclear inelastic scattering. And
Thank you very much, Alberto, for this very nice, interesting talk. Also regarding particular, I'm very, let's say, interested also in the last part, these vibrational modes probed by Mössbauer. This is very new for me, at least. The session is open for questions. Yes, Mark, please.
So thank you for presentation. In the case of your study on the iron 4, you show a Mössbauer spectrum, and you mentioned that you are fitted with Gaussian lines, Gaussian distribution, and you concluded that there was some kind of change of 0.4. Yeah, how did you conclude this?
Because yes, we considered these Gaussian distributions in the quadrupole splitting. So from the formula of the quadrupole splitting, then we considered how much this distribution translated into a higher value of the iron ligand distance. Also, by means of DFT, but from one hand, just simply from the formula of the quadrupole splitting, but also we confirmed this with ab initio molecular dynamics calculations made by theoreticians.
Curiosity, Alberto. I'm sorry, because unfortunately I need to exit and maybe I missed these details. I saw that in the last system that you described, you have basically an enriched system, 98% of iron 57. Just a question. Of course, I don't think that you do the synthesis of the system, correct? Okay, you know how they perform the synthesis, or you have some details about it? By Roberta, right? Okay. Okay. Then, so they prepare this.
They prepare this, yes. And they prepare this enriched in iron 57 specifically for the synthesis.
Yes, but I'm curious about this, the procedure. Maybe you can give me the contact, I can write them, maybe if I can.
Sure.
Thank you very much.
Other questions? Okay, do you have access to all the phonon dispersion curve, or do you have a filter in the frequency? I mean, acoustic and optical branches?
Well, the filter, I would say, is the energy range that I have shown. Then that is the range that where we could measure.
Okay.
I don't know. Maybe we could go lower or higher, but since we expected to have modes only there, we stayed there.
Okay, so you can focus on select the range where you expect to have. Okay. Thank you.
Okay.
No other questions? So let's thank Alberto and all the speakers.